And you can rename itself to ACP or cluster or something.
Live has started.
Toby, what's the Toby, what's the
So I think today there's a bit of a difference. Mute ourselves first.
Yeah. And now we can ask if people are hearing us.
Should I try?
Are people hearing us?
Yeah.
Remotely, I mean.
Okay.
Oh, are we using that expression? No, we should use the other feature. What's the magic? We should use the default. This one. Right. Now into the right.
Okay.
Now everything should be working correctly. Into the well.
Except for, so can you also hear me now? If I talk like this? Okay. Cool.
You ready?
Yep.
Should we start?
Yeah, sure, let's start.
Hello, everyone. Good morning. Thanks for coming on the morning section of today. Our first speaker for today is Levin Hornischer. He will talk to us about dynamical systems via domains.
Exactly, yeah. So good morning, everyone. Well, thanks for being here this in the first session. Thanks for having me and for this opportunity to talk here today. It's a really nice conference. I'm really enjoying it. So exactly, I'm going to talk about dynamical systems. That's the word, yeah. Dynamical systems via domains. That's based on my PhD. Well, I can actually take this off. It's based on my PhD thesis. And so let me start by just motivating what I'll talk about. And for that, let's go back to sort of the end of the 1960s when domain theory was started to be developed, and that has been developed as sort of a mathematical theory for computation, with the idea being that we would like to have a way to assign, if we have a programming language and we have a piece of program written in there, so that's just a syntactic object, so we would like to be able to explain what that piece of program code does by mapping it to the mathematical function that it computes. So that we can somehow explain what the program is doing by mapping it to the right kind of mathematical structures. And this should be done in a systematic way so that certain program constructions would correspond to certain mathematical operations, and this all nicely lines up. We could call that sort of computation with the regular programming languages. We could call that symbolic computation to contrast that with what we're seeing in AI these days, where we would have neural networks or machine learning, where we have neural networks that also somehow compute, but they don't compute symbolically in a real sense anymore, because now you only have like vectors of real numbers and gradient descent and all these kind of things. So you don't really have clear symbols anymore. And that's in a way precisely this black box problem of AI, that you cannot really tell anymore what those numbers are standing for. And what we want to do today is to see whether we can extend this idea of a domain theoretic semantics to non-symbolic computation as well. That's going to be the goal. So like in a sort of in a broad sense of an effort of explainability, so will be more of a structural top-down explainability rather than what you would see sort of in explainable AI as a field where you have all kinds of methods to have where you would have a given trained neural network and you would try to concretely explain why it gave a particular output by saying like which features of the input were important. So these are other methods. This is like more of a structural approach, I guess. Before we start doing that, we should say a bit what non-symbolic computation really is. And so just like to say what a program is in a programming language that somehow specifies a computation, we should say how non-symbolic computation is specified here. And I think it's quite fruitful to think about that as a dynamical system. So a dynamical system contains or consists of a state space and the semantics. And we can think of the states as somehow the computational states that, for example, a computer could be in. But in general, it could just be any abstract state space. And we have a dynamics that tells us how we go from one state to the next state, just like a program would do on a regular computer. And this means that our task is to somehow build for a given system a domain, and I'll explain more what that is, that somehow describes the behavior of the system, right? So this is what we want to do, and the goal that we would like to prove is that we have a certain adjunction. So we could start with dynamical systems, and based on observing them, we build a structure that I'll call a dynamical domain, which is a structure in the sense of domain theory, so a certain partial order with some more structure on it. And then we can also go in the other direction once we have a dynamical domain, that it somehow models a dynamical system, so we can go back again. And these two constructions should be adjoined. So this will be the main result and the goal that we're working towards, so that we can be really sure that these domains in a satisfying way somehow represent or explain or mirror what dynamical systems are doing in a very different kind of mathematical structure. Okay, so that will be the goal. And the outline for the talk is that I'll first say what dynamical systems are and have like a little bit of a crash course on domain theory, but you don't need to know much about that. I'll then outline how we can go from systems to domains, so this observation direction. And then I'll introduce these dynamical domains independently as a mathematical structure in their own right. And then sketch how we can go back from domains to systems. And then in the end, show that we have an adjunction. Okay, so let's start with dynamical systems. So I'm sure many of you have seen them at some point. There are many different formal notions of dynamical systems. Here I'll be using a very general one, where a dynamical system consists of, again, out of a state space and a dynamics. In the state space, we assume to be a probability space. And for some more technical reason, we assume it to be standard Borel. So we exclude some pathological probability spaces. And we assume that the dynamics is measurable. So the pre-image of a measurable set, so a set in the sigma algebra, is again measurable. And the more usual systems that are often studied, where you would additionally assume that the probability space is a Lebesgue space and that the dynamics is a measure preserving bijection. So measure preserving means that the pre-image of a measure has the same measure than the original set. And that is, if we talk about these systems, we will call them standard. And then these are studied in ergodic theory, so dynamical systems theory. There's a question, yeah?
So is there any time of any sort of time dependence on the dynamics? I mean, I guess usually I would expect to see a function from x across time to x.
Yeah. So here we assume time to be discrete, exactly. So that's so that the dynamics tells you a one-step update. Yeah. So you could have other notions of time where, especially continuous time, and then exactly you would have the setup that you have exactly that you have x cross time to x. But if you're in the discrete case. And if we think about computation, at least in this setup, just to make it a bit simpler, you would have discrete time to see how the dynamics goes, and you can think of that as somehow an approximation to a continuous dynamical system if you want to. Yeah. Exactly, and but the reason why I dropped the standardness assumption is because in this computational application that I had in mind, standardness seems too strong. So let's see that in one motivating example. Like sort of an abstract version of machine learning. So there we could think of a machine or like an AI model that we want to train. At each state of the training process, each stage, it's characterized by a set of parameters W. And then given some data or a bunch of data, we have a learning algorithm like backpropagation that would update these weights to a new set of weights, W prime. And we can think of that as a dynamical system if we'd say our state space consists out of the weights times the data sequences that we can observe. And then the dynamics would map a given weight and a data sequence along which we're learning to the updated weight and the rest of the data sequence. And here, if we had a measure in X that somehow describes the random initialization that we have and the data sampling process, then there's no reason why this should be preserved by T. So this is why we drop the measure preservation assumption, which is otherwise quite crucial in dynamical system theory. All right, so that's the kind of systems we will be working with. But since we're in a category theory conference, I should also tell you what amorphisms are. And they are usually defined as follows. So they are a function from one system to another. It's a partial function with a domain and codomain that is an invariant set of full measures. So it means if you're in there and you update or you use the dynamics, you're still in the set that's invariant, and full measure means you're measurable and you have probability 1. And those now should be measure preserving. So the preimage of a set should have the same measure as the original set, and they should be equivariant. So that means if you first update, or if you first do the dynamics and then map, it should be the same as first mapping and then updating. And this phi is called bijective if it's an isomorphism, and two morphisms are identified if they're identical on an invariant set of full measure. And the reason why you have this invariant set of full measure all the time around and the partial map is that since you're in a probability space setting, you would like to do everything modulo measure 0. So that's the reason for this a bit complicated looking definition at first. Right. So then maybe just a little bit of background on domain theory. So now that I told you what the systems are, so domains, if you haven't heard about it, I think that all that's on that slide is completely enough for the talk. So domains are certain partial orders. So partial orders that so a set with an order relation on it that have some additional nice properties. And the intuition behind them was that these elements of the order, they should somehow be the outputs of a computational process. And the order describes information containment between this. And an example would be, a standard example would be the set of all finite and infinite binary strings ordered by extension. So if we had some computational process that produces binary strings, then these could be the outputs. And if one string is an initial segment of another, then this is somehow informationally contained in the other string.
Is the intuition that this ordering is related to updates going to be correct, or
what kind of updates? The updates in the.
When you're saying that the order describes information containment, but somehow it's kind of like the parameters are being ordered.
So I would think on so the order is a fairly static thing. So that's just like information containment, and the dynamics that we see coming from the system that we'll later on see that we'll add some additional domain theoretic structure which will take care of the dynamics. But I'm not sure whether that answers the question.
Okay, the answer is probably not. Probably not.
Okay. But so okay, maybe we can talk about that after the talk a bit more. Cool, thanks. And exactly, so and you can also think of sort of the finite binary strings as sort of the real elements that are somehow accessible because they're finite, and the infinite binary strings, which are the maximum elements in that order, as somehow the ideal elements that these finite elements are modeling. Right. So, but if you want to see some more formal definitions, I'll also have this slide. So call a DCPO or directed complete partial order is a partial order where every directed subset has the least upper bound. It's also called join, or maybe sometimes limit, where a directed subset is a non-empty subset such that for any two elements in there, you have an other element in that set which is above the two. So they are somehow the consistent sets. And they importantly also have a topology, the Scott topology, named after Dana Scott, who was very influential in developing domain theory. So a set is Scott open if it's an upset. So if you're in there, anything above it is still in there. And it's somehow inaccessible by these limits. So if you have a directed set and whose join is in the set, and actually already some element of that set was in there. And then to function between two DCPOs is Scott continuous. So continuous with respect to the topology if and only if it's monotone and preserves directed joins. And the Scott domain is a particular domain. So the word domain depends a bit on which context you're in. So usually you always assume it's a DCPO, and then depending on the context, you might need additional properties. And we will be talking about Scott domains. So there you assume it's a DCPO, which is non-empty, and then something called omega algebraic and bounded complete. But we don't need those notions for now. They're just they make them particularly nice. Right. So that's just a bit of background. So now I want to go and see how we can go from systems to domains, and sort of first sketch the very high level idea you should keep in mind. So the idea is that if we're given a system X, we would like to construct this object D, which we will then call the dynamical domain of the system. And the idea is that somehow this D should consist out of basic elements or somehow finite elements, which represent observations that we can make about the system. And the higher you go in the domain, in the order, the more fine-grained they become, these observations. And then somehow we also have limit elements of these basic elements, so just like the infinite binary strings. And we have some additional domains theoretic structure on this D, so the F, so that we can also induce the dynamics on these limit elements. And then this should form a system modeled by this domain. And that system we would like to be isomorphic to the system that we started out with. Right. So that's the high level idea. And I now want to spell this out in a bit more detail so we can appreciate a bit more what's actually going on. Just give an eye on the time. Right. So to do that, we should first say what sort of this intuitive notion of observation should mean. And here I use a particularly simple notion. So any measurable subset, I guess the clue is in the name, we can think of that as a measurement or an observation that we can do. So thinking of like if a state is in that set, that means that if you would then perform that measurement, it would come out positive. And then if we have a finite set of measurable subsets, so finite cover, meaning that any state is at least in one of these measurements, then we get what we could call maybe the observed system that reflects the original one. So if we had our original system here with two states whose successor states are given like that through the dynamics, then we can think of if we had this finite cover, in this case, just a partition into 4 cells, then we can think of, okay, so what we see, at least through our measurements, we can see that we can jump from this cell to that cell, meaning that if we make this measurement now and the state happen to be here, then we will make this measurement next. And similarly, we can jump from this partition cell to that one, and there might be more in here. So we somehow have like a now non-deterministic but discrete reflection of what the original system was doing using such a cover. And then we can, of course, see like if we would fix one state and sort of follow what's called the orbit, so you keep applying the dynamics and see how it jumps through the state space, then we would correspondingly get a sequence of these cells and see how we jump through the system. And to make this a bit more formal, we could call an observation parameter I to consist out of a number n, which is the number of steps that we will observe the system, and the c, which is the measurements that we can do. And then if we have a particular state, we can see which of these jumps through the system or through the observed system it can realize. And these are somehow the observations that we can make if the system happened to be in that state X. So you can think of them as in a very hand-wavy way as sort of the possible observations. So one such OI of X would be possible observation. Right, and then it makes sense to consider the set of these. So call that HI, set of observable behaviors. And so this is a finite set. And it also has a natural dynamics on it, where we have one observation and then we would map it to the observations from the next state. But the problem is that this is not a function. So you could this way map to several successors. And then there's a trick in domain theory that whenever you have a function which is actually a multifunction, so not deterministic, there's a concept called Smithe power domain, and that deals with non-deterministic processes. So we can use that here. And in this case, it's just really the set of non-empty subsets of this HI ordered by reverse inclusion. And this forms a finite Scott domain. And then our original idea for the dynamics then lifts up here by just saying that, well, we map M, so a set of these behaviors, to all the successors of these behaviors. And so this now becomes a deterministic, like a real function, and it's also Scott continuous. And we also have some domain theoretic analog of a probability measure, so that's evaluation, where we say, and this is generated by thinking of, okay, so one such behavior, what's the value of it or the probability of it? Well, it's a probability in the system now of all the states that give rise to the same behavior, same observable behavior. And so then this is evaluation. And so now we have the structure here, DI, consisting out of a finite Scott domain, evaluation, and this function. And this was with respect to this one fixed observation parameter I. And now I guess can probably already guess where this is going now. So now we would like to refine these observation parameters to somehow finer observations. And then as we keep refining this, take the limit of these DI, and hoping that that limit object will be the dynamical domain that models our original system. And so I'll tell you now how this is done. And just a little quick disclaimer. So we actually won't use all of the measurable subsets that are available, but we will only allow measurements eventually from a countable subset B that in some sense generates all the other measurable sets. So this will just help to make things countable. And for now, we could just say that we'll fix such a subset, call it a basis if it's closed under finite intersection. So just fix a subset B, which is closed under finite intersection. And we then write I of B for the set of observations parameters that you can build with that set. So for all those I's where the cover comes from sets in B or measurements in B. Okay, and then, so what should that notion of refinement be? So here is if you have a parameter, observation parameter NC, so I equals NC and J equals MD, then if we want to say that J refines I, we mean that the observation time increased and the usual definition of the cover D being finer than the cover C, which means that every set in D is a subset of some set in C. And we actually need some additional condition, a bit more for some more technical reason, which would say that any state in a set of C, for that we can find a set in D such that the state is in D and D is a subset of C. And then can show that this set of observation parameters with this order is a directed pre-order. So first ingredient of a diagram. And we also have some natural maps going from the finer observation domain to the coarser one by just mapping an observation with a finer measurement to the corresponding observation that we would do with a coarser measurement. And so now we have all the ingredients to a diagram. So we have our objects and our functions here. And we would like to take the limit of this. But of course, we have to somehow specify in which category we are doing this, that I haven't told you yet. And for that, we will now move to this category of dynamical domains. And this will be the category in which we will take the limit. So that's the next section. So this is what I just said. So so now I would like to define this category DDOM of dynamical domains. And I'll define it in a typical domain theoretic way. So just independently of the system. So we just have this mathematical structure in their own right and not sneak in system terminology. So for that, I'll tell you a little bit about what is sort of a typical approach in domain theory to define a category of domains. So I'll do this for this category, which are called bifinite domains. They're not important for us now, but they illustrate what's going on. And so everything in green is for this example of bifinite domains, and then forget about the green stuff. And then we have the recipe for defining a category of domains. And so what we do is we fix a background category to start out with of domains. And in the case of these bifinite domains, this will be the category of DCPOs with the least element, so least element in the order, together with the Scott continuous functions. And then we use a subscript F if we want to restrict to the full subcategory of finite domains, so where the underlying set of the order is finite. And we use a superscript P if we want to restrict to the wide subcategory where all the morphisms are additionally also projections. So projections means you're not only a Scott continuous function, but you're in order, an adjunction in the order sense. So this means you and you're surjective. So you have a projection from the bigger domain to the smaller one, which is surjective, and it has a corresponding embedding in the other direction. So that means that you can, if you go down and then you embed, you're below to where you started, and if you first embed and then go down again, you're exactly where you started out with. So this is just this technical notion of a projection on top of being Scott continuous. So this if you don't know about them, you don't really need them. It's just a restriction that you need here. So the next step would be that you define an expanding system as a diagram now in this restricted category CFP. And this diagram might also be required to have additional properties. So in the case of bifinite domains, it is that the index set should be directed. And then the main work is to show that these expanding systems have limits in this category CP. So the limits could now be infinite. And then to finish things off, you define your desired category. So in this case, the category of bifinite domains as the full subcategory of your background category, where the objects are limits of expanding systems, and you keep the same morphisms around. So the morphisms are no longer required to be projections here. All right, so this is it's a standard way, domain theoretic way of defining a category of domains. And we now want to follow this without the green stuff for our dynamical domains. All right. So to define the background category, I'll say what call these the objects in their dynamical DCPO. So they are just triples that we've seen before of a DCPO continuous valuation. So that assigns Scott open sets values between 0 and infinity and the function f, which is Scott continuous. And the idea being that this valuation is somehow a counterpart to a probability measure, and the function f is somehow a counterpart to a dynamics. And we also will call this the dynamical Scott domain if additionally this domain is a Scott domain, and this valuation is a bit of a technical term, what I call max normalized. So it's more like a probability measure in that the whole domain has value 1, and the maximum elements are countable intersection of Scott opens with value 1. That's just to make it a little bit closer to dynamical systems yet, but still not all the way there. But it works as a background category. And then the dynamical morphisms, so the morphisms between these dynamical DCPOs, they are functions on the underlying domains that are Scott continuous and then have additional 4 properties, which are also maybe a bit technical, but so they should be max preserving. So that means if you're a maximal element in the first domain, then the image is still a maximal element, which has to do with the idea that these maximal elements are somehow the limit elements that are modeled by the domain. So this should be preserved. Then maybe the most technical notion of being maxed by assimilative, meaning that if you're in here, you map over there and you're below a maximal element, then you should find a maximal element over here to which you map there. So this is a bit similar to this notion of a bisimulation that you would have in modal logic, for example, hence the name. And then one standard condition that the valuation should be preserved, and then being equivariant, but now actually only semi-equivariant, so only one direction holds. So if you first apply the dynamics and then map, you're bigger than first mapping and then applying the dynamics. And also only for the maximum elements. So this is, so some of these are a bit technical. It just turns out that this is in the end the right notion of a morphism. But this forms now our background category. So dynamical Scott domains with dynamical morphisms. And so the next step that we have to do is I have to tell you what an expanding system should be. And this will be a diagram in this category or background category, now restricted to finite and finite objects and projections, where the additional properties are that first it should be a countable directed preorder, the index set, and the diagram should be what I call upward deterministic. The intuition says that somehow if you take a dynamics fi, so it's at step I, and it fails on an input ai to uniquely pick out a maximal element above it, so there could be 2, then we can go to a high enough j where there will be only one. And more formally, this spelled out like this, but it's a bit of a mouthful, so I won't even attempt to read this. But so this one additional technical condition that you need. And then finally, we can then actually show this limit theorem so that the limit actually exists. And this goes as follows. So if we're given such an expanding system, then we build the underlying domain as usual. So just, yeah, the usual limit construction that you would have. And this forms the Scott domain. And we also have projections, which now are literally projections. And we also get that there is a unique max normalizing valuation, which commutes with the projections. So that's also nice. And then a bit more of a complicated condition is that there is a pointwise largest function on D that is Scott continuous max preserving. So maps maximal elements to maximal elements with this condition that it's always bigger than the corresponding dynamics at the index. And now, okay, so this will be our limit object, but in what sense is it limiting? So there's one little twist that we look at what we might call the restricted limit. So we now get a cone in the desired category. And the underlying object is max preserving, so that its function is maps maximal elements to maximal elements. And it is limiting not among all cones, that's actually not what we want, but it's limiting among all the cones that also have a max preserving domain. And so it's then there you have the usual definition. So it's restricted to that because we want, as I said earlier, we want that this dynamical domain should model a dynamical system on its maximal element. So we want that this limit is such that the function is max preserving. So we would want it to be the limit subject to the condition of being max preserving. So we take this notion of a restricted limit. You could also formulate that more generally, but so that you take a limit in a full subcategory, something like this. But yeah, this is all we need here. And of course, so the important example for us will be that this diagram that we constructed from observing a dynamical system, this will be such a diagram here. And just a few words on the proof. So this construction of the domain D, this is standard, as I've already mentioned. For the evaluation, there is also some existing work that you can use. It's fairly recent. But the difficulty is with this function f. So this is a bit of work to get that using quite a bit of domain theory. But so this is why I won't go into detail here. And then, okay, so this is, so we're almost there. So now we just need to define what our dynamical domains are. So we can, to finish this off, so we say the dynamical domain is a dynamical Scott domain, so an object of our background category that is the restricted limit of an expanding system. And then we can take the full subcategory of our background category existing of these objects, and we denoted it as ddom for dynamical domains. And the morphisms in there remain the same dynamical morphisms that we've seen before, so they're not required to be projections anymore. So this is now the definition of these dynamical domains just in their own right. So now to finish things off, we still need to go into the other direction, where we go from domains to systems. And here, this is fairly quick. So the theorem is that if we have a dynamical domain, so the idea will be that the maximal elements are those that are somehow modeled. So they're the ideal elements that are modeled by the real elements of the domain. And so we restrict to them. And the relative Scott topology on it is a compact zero-dimensional Polish space. Our function restricts to a continuous function on there because it is max preserving. This was the whole point. And the valuation determines a probability measure in a canonical way on the sigma Borel sets, or Borel sigma algebra. And so then we get this dynamical system consisting out of the maximum points, this Borel sigma algebra, the measure, and the continuous function. Okay, so then what's left is to put all the things together and see that we get a junction indeed. And so let's first formulate it on the object level, and then we'll see how it works on in general. So on the object level, if we start with a dynamical system and we take some countable basis, which we demand to be separating. So separating means for any two distinct states, there is some set in B such that one state is in there and the other isn't. And that's in a way saying that it generates the whole measurable sets. But so with this assumption that we're a standard Borel space, these spaces will always exist. And then we build this diagram as I outlined before from observing the system. So we get this diagram and these projections. And this indeed then forms an expanding system. So that's something to be shown. And so we can take the limit of it. We could call this the observation domain. And so this is this dynamical domain obtained as a restricted limit. And then we have a canonical embedding from the original system into the system modeled by that domain, which maps a state of the original system to the sequence of observations that the state gives rise to. So this, and then this can be shown to be an isomorphism of dynamical systems. So then this means if we start with a system, go to a dynamical domain, go back, we start with a system that's isomorphic to where we started out with. But that's on the object level. So to finish things off as a junction, we would like that these two operations, observing and modeling, should be adjoined. And to do that, we'll work in this to state this precisely in the category of topological systems. So not all dynamical systems, but the topological ones. So that will be easier to state and a bit more clean. So there the objects are just as before. Now a state space is a topological space with a probability measure on it. So a zero-dimensional compact Polish space, probability measure on it, and a continuous dynamics. And the morphisms now are just continuous measure preserving and equivariant functions. And what we've just shown, essentially, this theorem that we just had, is that every dynamical system is realized by such a topological system, right? So the system modeled by a domain, if we use the topology, is such a topological system. And then if you forget about the topology and only use the Borel sigma algebra, we get the system back that's isomorphic to where we started. So these kind of topological realization results are known in ergodic theory. An important one of them is the Jewett-Grieger theorem. But so with these caveats in place, we do indeed get the desired adjunction. So that if we start with a system, build the dynamical domain, and then go back to what's modeled, then we do get the adjunction that we would like to have. And just 2 comments on this. So now working with these zero-dimensional topological systems, there we have a natural choice or canonical choice of basis, because we can take all the clopin subsets, so the sets that are both closed and open. So that makes it more convenient. And we can also restrict all of this to an equivalence, because we know when we start here on the left side, go to the right and go back, we're isomorphic to where we started. But if we start on the right side, go to a system and then back, we not necessarily need to be isomorphic, but if we additionally put some simple domain theoretic conditions on our domain, we actually get an equivalence. All right. So there is a bit of a more detailed picture, just to sort of outline how this would look like. So we've seen now the adjunction here in the middle or in the diagonal. This upper side here, this would be the equivalence that I just mentioned that you additionally get. And this bottom layer describes the connection, how these topological systems are related to these dynamical systems in the general sense. And this is through a localization and a compactification functor. But yeah, so that's a bit more of a bigger picture that's surrounding here, but I won't go into the details here. So let me finish by, I guess I'm in time still, right? Yeah. By an outlook. So all I've said now can also be extended to standard dynamical systems, so the ones that you would meet in ergodic theory. You then just always need to keep adding certain additional conditions to restrict everything in the appropriate way. And then sort of for future work, of course, you would like to reap the benefits of this adjunction. So you now can study dynamical systems through this rich domain theory and one place where I started doing this would be the notion of entropy. That's important for dynamical systems, and then it has a domain theoretic counterpart, for example, but there's much more to be done. And in a more philosophical mood, maybe this also invites you to reflect on sort of how symbolic and non-symbolic computation is related, because now one result is that in a sense, this non-symbolic computation in the sense of dynamical systems is now in a way a limit of symbolic computation. If you think of the finite dynamical Scott domains as being somehow, I mean, they're finite discrete structures, in that sense symbolic, and the limit of them is this then sort of non-symbolic structure. So you might call it pro-finite symbolic computation, I guess. But of course, so that like whether it's also stronger in any computational sense would depend on whether this limit process is in a sense effective, right? So because I mean, if you would compare that to what Turing did about computable real numbers, then there are certain real numbers that are the effective limit of the, for example, the rationals. They would also be considered computable. So that doesn't mean necessarily that non-symbolic computation is now super Turing computable or anything like that. So that's just the structural result. And you may ask some further questions. So I'll just pick three here. So one would be about you could now develop a computability theory for non-symbolic computation via what's called effective domain theory. So domain theory, where you, on top of not just knowing what are the continuous functions, you also have a notion of effective computability. So you can do computability theory and complexity theory in there. And you can, so that's some further work that could be explored. You could also explore just this category of dynamical domains. So you can ask about what are the domain constructions that you can do in there. Can you solve domain equations? So that's the usual stuff that you would do in domain theory. You could ask about, is there a universal domain? So that's something like the universal non-symbolic computation. So just sort of the analog of a universal Turing machine, I guess. You could just in general see what its categorical structure is to have like maybe an idea of what the type structure of non-symbolic computation is, etc. So, and another last open question that I'll mention is you could also try and use a finer notion of observation. So now our notion of observation was just a measurable subset, but you could also think about taking real valued functions. That's maybe more familiar in physics. So that's, for example, used in this operator theoretic approach to ergodic theory. Yeah, and I bet there's a lot more that you also think of, but let me just end with a quick summary. So our goal was to extend this domain theoretic semantics to non-symbolic computation. We were thinking of non-symbolic computation in terms of dynamical systems. If you don't like this interpretation, you can also just take this talk to be about dynamical systems because they're important in their own. I then introduced this category of dynamical domains as an independently defined mathematical object. And then we had this adjunction that we can go from dynamical systems through observations to these dynamical domains and go back to the model system. All right, that's it. Thank you.
Thanks. Any questions from the audience?
So I couldn't help but noticing that your definition of domain, that your dynamical domain, looked very similar to a notion of abstraction that is using more applied mathematics from the systems to context to model it properly. Do you see a difference, or can we take the category of dynamical domain as and name it as a category of abstraction?
It's a good question. I'm not sure whether people online heard it. The quick question was, or like to summarize it, whether you could think of these dynamical domains as somehow abstracting what the original system was doing. So it's somehow more tractable in a way. Yeah, I think that's a very really like the question. So certainly the finite objects that you take the limit of, I mean, they certainly are discrete things that are in a way abstracting what the original system is doing. So when you think of this picture I had a while back, where you think of this state space being partitioned, and then you just see what the system does by just seeing how these partition cells move. So that's, I would certainly think in terms of abstraction, yeah. But I'm not sure, yeah, maybe there needs, maybe we can talk more about this to understand also, so I can understand better what this notion of abstraction would be that you had in mind, because I think there should be a bit more to it than just this, but certainly was a motivating idea, yeah. Thank you.
So these dynamical systems, they're maybe I'm overstepping, but they're essentially coalgebras in some kind of category of probability spaces. But they're coalgebras for the Enrichment function. Can you maybe, like, is there any hope for getting similar results for coalgebras for more complicated functors? So that is, yeah. So I think this is a very good intuition. So I don't know too much about coalgebras, but certainly, yeah, like I mean, many of, depending on which functor you use to define your coalgebra, I think you also at least get the notion of maybe label transition system out. And so it would be very interesting to see whether this also works in this more probabilistic setting. I'm not quite sure whether you would then get whether your coalgebra would then determine which function or like which properties the dynamic should have, whether you can handle that. But yeah, that would be definitely interesting to explore, because it would be a nice, more general setup. And in general, I guess, like, I mean, there's also in category theory, so Levin wrote on this, like a more general notion of a dynamical system in a category theory context. So it would also be a natural question to see whether you can do the whole process in this more general setting. Yeah. Thanks. Yeah.
Okay, let's thank the speaker again. Okay.
You're introducing the dynamics so nicely.
Yeah, yeah. I looked at your numbers. Really excited to hear it now.
Oh, yeah, I would love to know the connections between, because there's a lot of stuff in this more like ergodic world that I don't know much about.
Yeah.
I don't know how to attach this properly.
I don't know either.
Is
I
it
think
like
you just have to clip it. I think let me do the try. This is looking the other way around.
Is it pointing downwards?
Yeah, it's pointing downwards.
Yeah, that seems strange.
How did this happen? How did you do it?
So I had
yours is very odd. Oh, you have a proper shot.
Yeah, maybe
I can't.
So when we
maybe
clip it, it's turning down.
to the
To the
your-
thingy.
Oh, we can
yeah.
touch it.
That's a good idea.
Very good idea.
It's fine.
Maybe it feels like it's gonna. No, maybe not.
Yeah, just
Or maybe, yeah, just
make
this
sure
here,
it's gonna
Like
be-
that?
yeah.
That's
Super
fine.
nice.
Okay. Okay. Can everybody hear me? Yes. Maybe? Yes.
Okay, so we're ready for our next speaker for today. It's Toby Clere Smithe, and he will talk to us about open dynamical systems as polynomial coalgebras.
Yes. I think I've got this. Okay, good. Okay, thanks everybody for being here. Thanks for having me, and thanks to Levin, wherever he's gone, for the great introduction to dynamical systems, which is going to make my life a bit easier. So, okay, right. So for a long time, I've been working on functors that try to turn these kind of Bayesian lens things into dynamical systems that seem to mirror some of the structure that we get in bits of the brain, like visual cortex, where people think we've got these kind of bidirectional things, that there's kind of forwards projection of information and backwards projection of information. It's trying to minimize some kind of prediction error. And this thing all happens in time. There's signals coming in, there's stuff being updated all in time. And so you need a kind of a nice category of dynamics, a place to do kind of what I think of as dynamical semantics. And the thing is, these things have, inputs that go forwards, and inputs that go backwards, and outputs that go forwards, and outputs that go backwards. And that means they have this particular kind of bidirectional compositional structure. And so to have a functor that goes from the left here to the right, you need a kind of semantics category which has a similar kind of compositional structure. And so that's what I'm going to be talking about today. Okay, but first of all, and luckily I won't need to spend too long on it, I'm going to talk about something that I call closed dynamical systems, which is really the same notion of dynamical system that Levin was talking about earlier. My setting will be a little bit more general, but effectively it's the same kind of thing. And then the interfaces, so the things that are going to be these types on the domain and codomain, or at least a generalization of them, are going to be given by polynomial functors. I've been inspired by David and colleagues' work on all of that. And so then I'm going to say how to use these two ingredients to give a notion of open dynamical system, which is deterministic. And then to relate to the question that you asked, Ezra, I'm going to talk about how we get to different kinds of transition systems. So they could be stochastic or non-deterministic or something like that. And with all of these ingredients, we can get to the kind of categories of dynamical systems which have the right compositional structure for the kind of semantics that I was interested in. Okay, and so this notion of dynamical system, it's really the same thing, as I say, that Levin was talking about. I'm going to be living in this slightly more explicitly categorical world. And so, yes, it's an action of a monoid, which we think of as representing time, on something which we think of as a space. And so we have these rules that, if you don't evolve the system, there's no change. And if you evolve through time t and then through time s, this is the same as evolving through t plus s. But these rules are really just the rules of composition. And this says that this theta preserves composition, which means it's a functor. And it's in particular a functor from the de-looping of this monoid. So that's the category with one object, and for each point in time, or at least each duration in time, a morphism, and composition is just summing intervals. And so this means that theta is just a functor from this de-looping category into the category E of spaces. I'm going to assume it's locally Cartesian closed. It's basically set, but it doesn't have to be. And we don't need all of that structure to do the kind of thing that I'll be talking about today. Okay, and this is just a picture of the function. At least I'm aware, I think this perspective originally goes back to Lorand's work. It's a kind of very behavioral perspective, because we don't actually, the objects aren't, they're not the, differential equations themselves or the vector fields, they're kind of their behaviors. So, as we saw in Levin's talk, in discrete time, a system is really just a transition map. So you just iterate this map. That the sort of monoid action rules force it to be like this. But in continuous time, yes, you get something a bit more complicated. So you can have the solutions to the differential equations. They give you, for each initial condition, an evolution of the system in time. And so you get a map, which is, you get this family of, time indexed maps. Okay, and so what about other kinds of transitional systems? For the kind of thing that I was talking about at the beginning, for predictive coding, we need at least stochastic systems. Often, at least in the world that I'm thinking about, these things are kind of Markov processes. And the way I might model the behaviors, or for these kinds of systems, is by changing this category E to the classic category of some monad. In particular, the case that I'm thinking about is the case where this monad is, say, the distribution monad, finitely supported distributions or something like that, or whatever your favorite probability monad might be. And in this case, a functor from this de-looping category into the classic category of this distribution monad is something that we might call a closed Markov semigroup. In particular, every closed Markov process gives rise to one of these things. You can write down what the sort of compositionality rule means. It just says that if you start at x and then at time t, you get to some point, and then you go from that point with some probability over to some point y, and that takes you this time s. Then the probability that you're in y after starting in x is really just this integral over all these intermediate points and their probabilities. Yeah, so as I say, every Markov process induces one of these semigroups. I don't think it's the case that you can go the other direction. Maybe in a particularly nice restricted way you could, but it doesn't really matter for me. It's just useful that we have these categories, this kind of representation of these things. And yes, we've seen that if you have one of these things in discrete time, it's a coalgebra of this functor M. And really, when I say M coalgebra, I just mean a map, say, x to mx like this. Okay, so that's enough of the kind of dynamical systems background. I'm sorry it's so fast, it kind of has to be. I need to talk a little bit about polynomial functors. These things, as I mentioned earlier, are going to model the interfaces of our systems. So what is a polynomial functor? It's a coproduct of representable coprecives. I'm going to, as I say, write E for this ambient category. And as I mentioned earlier, I'm going to assume often that it's locally Cartesian closed, but at no point do I require to all of the locally Cartesian closed structure, and all of the structure I do use will appear in a kind of slightly more general way later. I'm going to write y to the a for this representable copreciv of a following Spivak's work. This y is kind of, you can think of it as Ionada, so this is like the Ionada embedding. And so we write this general polynomial p. It's a coproduct, so it's a sum of these things. It's a sum of a p of 1. If you put 1 into this functor, so it's a functor e to e, it being a copreciv, you get this indexing object or set. And for each summand, you get this y to the pi, where it's indexed by this I. So this pi is the representing object, as I say, for the ith summand. And I think of this type p of 1 as the set or space or type of possible configurations the system could adopt. Like, I could be standing up here waving my arms around, or I could be blinking my eyes, and that they might be different configurations. And in each different configuration, I might receive different kinds of input signals. And so this type pi is a type of admissible input. So for instance, if I've closed my eyes, then I get different kinds of inputs than if I open them. And okay, so we've got these things, they kind of represent boxes. So if I have this thing with yc inputs and bz outputs, I could write this as bz y to the yc, because yc is inputs. And I can put these boxes next to each other. So I've got this tensor. And these things are nice because they're kind of these little monomials. You can do this with more general sort of dependent things. So as I've mentioned with my eye blinking, I might have different kinds of inputs. And I can do wiring of systems using the morphisms of polynomials. So what is a morphism? It's a pair of a forwards map. It says where do the kind of configurations get mapped to what, we could think of these maybe as outputs of systems. And then for each position in P, I get a way of sort of taking the inputs from Q back to inputs of P. So for instance, I need a way to say, I need to map this Y input to something in this internal box here. And so that's kind of going backwards from this thing here to this thing here. And a nice way of writing down this category is to say that it's the category of dependent lenses in E, which means that it's the Grothendieck construction of the pointwise opposite of the self-indexing. And I'm not going to spell that out because there are lots of places you can read about it, in particular in David and Nelson's book, or I sketch it in the paper I've submitted. And on objects, what is this tensor? How does it work? Okay, well, it's given by just multiplying, taking the product of the types of configurations, and for each pair of configurations, the type of possible inputs in that pair of configurations. And it works similarly on morphisms. So you just take the product of the backward and the forward maps. Okay, we need a little bit more structure before we can give the sort of nice definition that I want to give. There's this tensor, its unit is just y. It's quite easy to see that. It has a corresponding internal HOM. Okay, this behaves just like a normal internal HOM, so it satisfies this adjunction. And what does it work? How does it work explicitly? Well, on objects, the configurations of the internal HOM are these kind of morphisms, and then in the backwards direction, the inputs are a position and a kind of input in the sort of Q system. And we have these two nice facts. If you have AY to Y, it's the same as Y to the A. And morphisms P to Y correspond to sections of the projection. You can write this polynomial as a bundle, and then morphisms P to Y are sections of it. One more bit of structure I need is that composition, so we can, these things are functors and we can compose them, and this gives us a monoidal structure. It really just works by substituting. So if you've got Q compose or substitute P, that's just substitute P for every instance of Y in Q. Okay, and then the sort of amazing fact is that the comonoids for this substitution product are just categories. The co-unit encodes identities, the co-multiplication encodes codomains and composites, and the homomorphisms of these things are called cofunctors, and we'll hear, I'm sure, more about these in the talk by Bryce and Matthew on enriched lenses later. And as I say, if you want a great exposition of all of these details, which is a lot less hasty than my introduction just now, then see David and Nelson's book. Okay, so with all that out the way, a deterministic open dynamical system is a special kind of, with time t and an interface p is a special kind of morphism of polynomials, sy to the s, into this internal hom from ty to p, such that this composite morphism for any section of P, this gives you the inputs for each possible configuration. It's a choice of, say, way of closing off a system, such that this thing is a comonoid homomorphism. So what does this mean? Okay, so beta, this open dynamical system, is by the tensor homojunction, it's equivalently a morphism ty tensor sy to the s into P, which means it's a pair beta to the beta O, beta U, which I think of as output map. So that's a time index output map. So T times S to P1. And I think there was a question about indexing these things by time earlier. And then a sort of time indexed family of update maps. So for each state and for each possible input, you get a new state over time. This thing is a comonoid. What is it? It's the codiscrete groupoid on S. So it's got all the points. And for each pair of points, you get an invertible morphism. And this y to the t thing is the de-looping, it's just a representation of this de-looping category. And the comonoid homomorphism rule that this satisfies says that for any section, for any choice of inputs for your dynamical system, this thing that I call the closure, which is just a closed dynamical system in this context given by sigma, it's a closed dynamical system on S. So this thing then, this beta sigma forms a functor in this functor category bt to e. And so that's what makes it not just a morphism of polynomials or a coalgebra, it's actually like a dynamical system because it satisfies this kind of monoid action, this semigroup or flow rule. Okay, so I've got two examples. So, you can do these things in discrete time, and in discrete time we can show, okay, that's just an output map and an update map, and there's no time indexing because of the same kind of induction property that we saw earlier. And then this thing is really just a coalgebra S to PS. If you write down what this is and unpack it, it gives you these two things. But you also get solutions to open, say, ordinary differential equations. And so say we've got this kind of open vector field, then you can show that this kind of induces kind of R coalgebra of this kind of RP coalgebra, this kind of form. So these things, okay, they're nice, they form a category. A morphism of them is a morphism of closed dynamical systems is a natural transformation like this. So it's a map on the state spaces that sort of commutes with the transitions. And so we take inspiration from this to give ourselves the morphisms of these kind of open dynamical systems using these things that I call the closures. So a morphism of open dynamical systems from theta to phi is a map of the state spaces again, such that for any section, so for any way of closing off the openness, this kind of naturality squares commute. Okay, and so that's nice. These things compose as functions or as morphisms in your base category. And the identity is just the identity map in a state space. And obviously, trivially, that satisfies this rule. And I call this category coal TEP. So there's lots of nice indexing there. Okay, and it's op indexed by these polynomials. So each object of this category is a morphism of polynomials. This internal Hom thing is a functor, and so in particular, and it's covariant in this position. So given a morphism of, say, phi from P to Q, we can reindex covariantly just by using that functoriality. And it's easy to show that if you have a morphism of systems in the sort of domain category of this reindexing, it gives you another morphism of systems in the codomain category. I mean, you just sort of pull back this diagram and you get another diagram which also commutes. And so this gives us an op index category. And so that's nice. It's nice, but it's not nice enough for me because it doesn't really have the kind of nice monoidal structure that I was interested in. It doesn't have this kind of nice typing. But before I move on to that, I'll just say that these things really are coalgebras. Why are they coalgebras? It's quite easy to show, again, that if you have sy to the s into q as a morphism of polynomials, if you just write this down, unpack it, it's the same as a map s to q of s. This is the thing I said earlier, that these deterministic systems in discrete time are these p coalgebras. This is the same thing, but also notice that this internal Hom is again a polynomial, and so we can substitute this thing for q, and then this is again a coalgebra just by this, and so this is a coalgebra s to typ internal Hom of s. So that's a kind of funky coalgebra, but not all of these coalgebras are sort of dynamical systems in the sense that I mentioned, because they don't have to satisfy this semi-group rule. Okay, I'll say a little bit about stochastic systems. The nice thing is that we can sort of unpack all the definitions and just stick this monad in the update map, and then change the axiom so that it induces a functor in the Kleise category of that monad. That's nice, but it's a bit sort of wordy. And so the thing we can do is say, okay, well, hold on. What if I change my category of polynomials? I had this kind of Grothendieck deconstruction representation of the category. I can sort of alter this so that the backwards maps, sort of the maps in the kind of fibers of this Grothendieck deconstruction, have this kind of side effects. The trouble is you don't get, it's not really like a proper category of polynomials because you don't have pi types, you don't have a nice internal Hom all the time. But the thing is, you have pi types enough, and you have enough of an internal Hom. In particular, you have internal Hom when the morphisms are deterministic, and that's kind of enough to make the definition. This one here, the one that I started with, it's enough to say this definition in that category, even if it doesn't really behave like a category of polynomials, but it's enough for me. And we can also make something that's called random dynamical systems work. I don't have time to say what that is, but if you know what a random dynamical system is, I sketch it out in the paper. Okay, so finally, getting on to how to set up the dynamical semantics for this predictive coding thing. We need this kind of hierarchical structure forwards and backwards. It's kind of the standard sort of open systems with monoidal categories thing that we see in applied category theory. So we're going to get one cells with type XA to YB. So the answer is to construct Hom polynomials like this internal Hom. And I think this is very similar to what Brandon and David have been doing, and we'll hear about later. And it's kind of like a generalization of Spivak's Operad org. And so we can define polynomials like this. So for morphisms A to B, we could say, okay, well, we've got this polynomial Hom AB to inputs in A, and this gives us a natural composition morphism, and we can obtain a bicategory. And in particular, when this underlying category C is a copy discard category, then we get this nice copy discard structure on the category of dynamical systems. So we can write down like something like Bayes' rule. Need to use by simulation because the quality of dynamical systems is a bit too strong. And we can sort of do this again for the kind of sort of dynamical dependent lenses where we just use the internal Hom. But we might want to consider other kinds of lenses like Bayesian lenses, and in particular, that's what I'm interested in for my predictive coding. And so we need to write a different kind of like Hom polynomial, and we can do that, and we get a similar kind of composition rule, which composes just like Bayesian lenses do. And then a dynamical system, a one cell in this bicategory, it's a bicategory because this Hom category is a category. A dynamical system is given by state space, a forwards output channel, that's what I wanted, a backwards output channel, also what I wanted, and an update map that does something like sort of updating of the sort of beliefs in the system. And so that's what I needed for predictive coding. And I've got this compositional active inference 2 paper, which will be coming out and spells that out all in lots of detail. The last thing I'll say is that we can go a lot kind of slightly further, and I haven't really explored this very much, but we can do similar things for categories of optics for those of you who like these things. We can, instead of having this sort of forwards and backwards inputs being the inputs of the polynomial, we can have this thing called a context of the optics, which is again just a way of sort of closing the optics off. And we can define sort of dynamical systems on polynomials which output optics and receive kind of context for optics. And we get a nice composition morphism. And I call these things, and I get a bicategory in the same kind of way. I call them cilia because these things are optics, and the ciliary muscles in your eye are the things that control like your lens. So that's nice. I wondered if these things might be useful for building like dynamical systems that play economic games, that observe what's going on out there and update their internal structure accordingly. Okay, so I'm done. I think I'm slightly over time, but to recap, we constructed these op index categories coal for something that is maybe a locally Cartesian closed category and general sort of time, and we can extend them to different kinds of transition types. We saw how they sort of generalize closed systems and how they sort of generalize these, how they constitute coalgebras. And then we constructed bicategories of dynamical systems that are useful for the kind of cybernetic applications that I'm interested in. And there are sort of lots and lots of open questions. So like, what are the connection to the monoidal streams I think we might be hearing about tomorrow by Elena and colleagues. I know that in discrete time, these categories there should be a P here for each polynomial or a topos, but I don't know if this is still true. I've been thinking about it, but I haven't had time to think about it too deeply, if it's still true in general. And it would be nice also to translate ideas from coalgebraic logic and make these things talk to each other. And in particular, finally, I'm not sure how this coalgebraic framework relates to the sort of the other kinds of frameworks for dynamics that we've seen before, say David Jasmeyer's double categories. There's lots of stuff to be thinking about. So thanks for listening. I hope you understood some of it.
For the very next talk, maybe there's time to have super quick question before we go to the last talk of today. Any questions? If none, then you have one?
This is perhaps a bit confused question, but when you have coalgebras and you take these coalgebras from your functors, somehow it's called as coalgebraic data type. They find type like we consider loop from a functor, and they start to describe how it takes time and
yeah.
So what would be the connection?
So in discrete time, the connection is just that these things just sort of are coalgebras of polynomials because the sort of action rules force this thing to kind of the time sort of goes away. And then in sort of general time, there are these kind of funny coalgebras of this internal Hom polynomial. And then, I mean, in discrete time, you can also put the kind of monad of side effects in there. And that's the kind of standard story. And the question that I'm really interested in is how does all the stuff we know about coalgebras and transition systems in discrete time, how does that translate to this kind of sort of dynamic setting? I expect it might. I would like to know about how these streams relate, for instance, but I don't know. Thanks.
Okay, let's thank the speaker again.
Hi, can I share my screen from, oh, hello? Cool.
Online talk? Or, yeah? The next talk is online. Oh, okay.
Completely online.
Okay, yeah, the color coding in the program is not able to display both online and the demo at the same time. Okay, I have to somehow then
Sorry, I wanted to share from my second device. Unfortunately, it also has my name. I think we're named the same thing.
You have to find her and unmute her.
We cannot hear you, Sophie. If you can hear us.
I can hear you.
Yeah, so we are trying to solve this.
Is there somewhere to turn on the volume?
Yeah. Should be.
What did I do yesterday?
It's also
Manage
not
both
broken.
folders.
Yeah, it's our problem here.
So what she's asking is that she's connected also via her iPad, which is a second device also named Sophie Libkind. She can hear us. And that needs, so she needs to be able to share from that device.
So this needs to become a host as well?
Yes. So both Sophies.
Maybe problem.
Yeah. No, it's weird that. I did put it on the right audio. So this is the.
Oh, right, you can't hear her at all.
Can you go to audio settings?
Oh, that's.
Audio settings. No.
Yeah, how did you do the talk from John?
Yeah, so it was the.
I don't know.
It was working yesterday.
Who set it up?
Yeah, so yesterday we just like touched things.
Yeah. It's,
We practiced this before.
Sophie, can you test
So
your
the
audio
standard
again?
procedure is turn it off and
Hello?
Okay.
Okay, that's good.
Yay. Oh, and I can share. Amazing.
Yeah. Okay, so the last talk for today's session is typed and stratified models with slice categories is going to be a demo by Sophie Libkind and joint work with Evan Patterson, James Fairbanks, Andrew Baas, and Micah Halter. So to you, Sophie.
Great, thanks so much. I'm really excited to be here. So the story of this work, I think, is really cool. It starts out with sort of noticing this pattern that comes up a lot in scientific modeling. And today we'll see two examples that particularly come from epidemiology. Then we use some like super basic tools from the applied category theory toolbox to formalize and really pin down what this pattern is. And then use algebraic Julia, which is a software ecosystem for applied category theory, to then sort of bring that to life and automate and implement these in code. So to start off with, what is a stratified model? So a stratified model is a model where your population is sliced in a bunch of different ways. So for example, here we have an example from Wu et al. In 2021, where they developed this model of malaria, where the population is sort of stratified by genetics, by where the mosquito is in its life cycle, by where things are in the landscape, so what location they're at, and also by their disease status. So if I'm an adult infected mosquito that lives in this spot with this genetics, I'll evolve differently than if I'm a larva that's susceptible that lives in this other place with these other genetics. So another really motivating example for us is this paper where they take a bunch of different disease models, so different ways that a disease can evolve, and a bunch of different movement models, so different ways that people move around to different places, and they stratify the disease model by the movement model to get these total models. And then compare all the different combinations to real world data to figure out which ones sort of are the most realistic. So for example, consider for our disease model, this SIR model. So here it's a differential equation where we have a susceptible, uninfected, and a recovered population. Susceptible people become infected when they come into contact with another infected person, and then infected people become recovered. For our movement model, you can consider something like this very, very basic flux model. So in this model, we have a bunch of different locations, and then people can move freely between them. And so then what the authors do is sort of by hand, they adjust sort of their disease model by this movement model to produce their stratified model. And so here in the stratified model, what we see is we have a susceptible, an infected, and a recovered population now for each location. And the dynamics evolve so that people are moving around between places and also evolving their disease state. So another example of a movement model would be this simple trip model. And in this one, it's a little more complicated than the flux. Each person has a home base, and then they can travel to different places from that home base. So for example, I live in San Francisco and I can travel to Berkeley and then back to San Francisco, and then I can travel from San Francisco, my home, to Strathclyde and then back, or sorry, Glasgow and back. So again, they stratified this disease model by this simple trip model, again by hand, to produce this total stratified model. And we can see now that the differential equation is getting quite, big and unwieldy. It would be great to be able to sort of automate this process. And again, we have sort of a susceptible, an infected, and a recovered population for every place that a person could live and currently be in. So again, a lot of populations going on here. In the paper, they consider the 2 movement models we talked about, as well as 3 different disease models, SIR, SIS, and Ross-McDonald, which is a standard model for vector-borne diseases. But you can imagine that if you want to consider a bunch more disease model or a bunch more movement models, this process of doing the stratification by hand starts to become sort of unwieldy and not scalable. And so what we're going to see in this talk today is sort of using applied category theory tools to automate this process. And to make it so that when you want to add a new disease model or new movement model, it's basically no extra work. Great. All right. So to get started, before we talk about stratified models, we have to talk about typed Petri nets. So for us in this talk today, our model class is going to be Petri nets, and we're going to be working in this category of whole grain Petri nets. So the objects of this category are diagrams of finite sets that look like this. So we have a set of places, a set of transitions, a set of input arcs, and a set of output arcs. So here's an example of a Petri net. It has 3 places, S, I, and R, representing a susceptible, infected, and recovered population. It has 2 transitions, sort of this infection transition, which takes as inputs a susceptible and an infected person, and then outputs 2 infected people. This recovery transition takes in 1 infected person and returns 1 recovered person. And the morphisms are going to be Attal maps, which are maps of diagrams of this shape that preserve the arities of the input and output arcs. Great. Okay, so a Petri net can actually represent a domain-specific type system. So for example, on the left here, we have this type system for infectious diseases. It has 1 sort of place type, everyone's sort of just one type of population, but 3 different transition types. So the purple one represents an interaction transition where we have sort of 2 people interacting and then 2 people getting returned. The yellow and the blue transitions represent sort of single changes for a particular person. The yellow transition represents a change in disease state, so something like going from infected to recovered, while the blue transition represents a change in strata or change in some other status, like your quarantine status, your age, where you live, something like that. On the right, we have a type system for vector-borne diseases. So here we have now 2 types of places, hosts and vectors. So here a vector-borne disease is something like malaria, where we have our hosts might be humans, our vectors might be mosquitoes. And here we have, for each of hosts and vectors, again, we have change in disease state, sort of these identity transformations, and then change in strata, something like where they are or their stage in the life cycle, something like that. And then we also have this interaction transition between hosts and vectors, because in a vector-borne disease, that's how the infection will occur between a host and a vector. So a typed Petri net is going to be an object of the slice category of Petri sliced over a particular type system. So if we consider our type system for infectious diseases, we can now take our SIR model and type it over that type system for infectious diseases. So our 3 places, there's only 1 choice for what type they are, but now we have some choices for the transitions. So the infection transition, where a susceptible and an infected person come into contact and the susceptible person becomes infected, is going to be of the interaction type because it has those 2 input arcs and 2 output arcs. For the recovery transition, we sort of have 2 choices. It could be either be the yellow or the blue transition, but here we're going to type it by the yellow transition because it does represent this sort of change in disease status. And for each of the SI and R populations, we're also going to have this identity transformation representing some change in other strata, something like a susceptible person can change their age or where they're currently visiting. As another example, let's consider this Petri net typed over this type system for vector-borne diseases. So here, this model is sort of an SIS model for a vector-borne disease. We have susceptible hosts and infected hosts, which are both of type host. We have susceptible vectors and infected vectors, both of type vectors. We have two interaction transitions, so two interactions typed by the interaction type, one in which a host infects a vector and one in which a vector infects a host. We also have these transitions representing the recovery of an infected host or the recovery of an infected vector, again, typed accordingly. And then again, these identity transformations, which represent some change in other status. And so one really cool thing about typed Petri nets is they can sort of create these guardrails against creating these like sort of silly or unrealistic models. So for example, these red transitions are things that are ruled out by our type system. This is good because they sort of don't make sense. So if we think about this transition, if it did exist, what it would say is we've turned a susceptible host into a susceptible vector. So a human has turned into a mosquito, which is extremely silly. We don't want that in our model. And good news for us, it's ruled out by our type system because there is no valid typing that would allow a transition from a host to a vector. This transition has sort of a mosquito infecting another mosquito. Again, that's ruled out by our type system. And that might be reasonable because in vector-borne diseases, normally infections occur between hosts and vectors. So this is the first of several advantages for these typed Petri nets. So the first is model checking. As we just saw, we can use our type system to rule out some very silly models. It can also facilitate high-level critiques of a model. So critiquing a type system is, in a sense, a critique of the models that are typed by it. So if you have a model that's typed by this type system for vector-borne diseases, a critique you might have is that it rules out pathways for vertical transmission between parents and offspring. So if that's important to your model, then this type system is not the thing you want. Third, features of the type system imply features of the model. So because in this type system, each transition has the same number of input and output arcs, we know that in any model typed by it, the total population will be conserved over time. And finally, it can provide guardrails for composition. So yesterday, John Baas told us about decorated and structured cospans, and we can in fact create a decorated or structured cospan category with these typed Petri nets instead of with ordinary Petri nets. And that would ensure that when we sort of glue two Petri nets together, we only identify species of the same type. So we wouldn't be able to identify like a vector, like a mosquito species with a human species in our composition. So finally, I'd like to talk about the implementation of these typed Petri nets in algebraic Petri. So let's take our example of this typed SIR model and see how we'll implement it in algebraic Petri, which is a library in the algebraic Julia system specifically for the composition of Petri nets. So assuming we've already defined our type system for the infectious disease, let's define our SIR model. So it's a labeled Petri net with 3 places, S, I, and R. And then we specify each of the interactions, each of the transitions, and we say what are its inputs places and what are its output places. Then to define this sort of typed model, we need to give a morphism from our SIR model into our type system. And this is given by an Atchit transformation. And for each of the places, the transitions, the input arcs, the output arcs in our SIR model, we're going to specify sort of what place transition interaction, input arc, output arc in our type system it will map to. And then finally, algebraic Petri and CATLAB will visualize our model for us. So this diagram was produced automatically by CATLAB and as you can sort of eyeball, does match the model we were going for. Great. So with that under our belt, we're now ready to talk about stratified models. So a product in the slice category is a stratified Petri net. So to see that, suppose we have our type system for infectious diseases again, and suppose we have a disease model that's sort of typed over that, as well as some sort of stratification scheme that's typed over that. So a stratification scheme could be something like quarantine, a model of quarantine status, or moving around, as we saw in that motivating example. people moving around. And so when we take the product in the slice category, that's the same as the pullback in Petri. And then we get this stratified model, which is again typed over our original type system. So let's do an example. So here we have our type system for infectious diseases. And on the bottom, we have this typed SIR model. And vertically now we have this typed quarantining model or typed isolation model. So here we have a population of quarantining or isolating individuals, a population of non-quarantining or non-isolating individuals. We have two transitions, which are typed by change in strata, which represent entering isolation and exiting isolation. We also have these two identity transformations, which represent a change in disease state without changing your quarantine status. And finally, we have an interaction transition between non-isolating people. And notice there's no symmetric one on the other side, because of course, the point of isolating is that you aren't interacting with others. So now we're going to take the pullback to get our stratified model, which is now up here. And to talk through it, the idea is sort of we're going to pair together every place and transition with the same type. So we end up with these 6 places representing susceptible people who are either isolating or not, infected people who are either isolating or not, and same for recovered. Now let's take a look at sort of the pairs of transitions. So for example, this entering isolation transition is paired with this identity transition for susceptible people, which corresponds to this transition in our stratified model, which says susceptible non-isolating people can turn into susceptible isolating people. And then we can also, of course, exit isolation. And we have the same for the for the infected and the recovered population. If we consider this recovery transition, it's going to pair with these two identity transitions to give us these two transitions in our stratified model, which corresponds to if you're in isolation, you can recover. If you're in not in isolation, you can also recover. And finally, we have this pairing of this infection interaction with this interaction between non-isolating individuals, which gives us this transition in our stratified model. And of course, because there's no symmetric transition on this side, there's no symmetric transition up here. So this is a sort of the story of stratified models. And next, I'd like to show you how we implement that in algebraic Julia. And I think it's actually very cool because it's just like a few lines of code using things that already exist in CATLAB. So we start with our typed SIR model, which we already saw the definition of on a previous slide. And we also have our typed quarantining model, which represents this vertical arrow. And now we just apply the pullback function from CATLAB to produce the pullback, which is going to return to us this span of Petri nets. Now, the apex of that span is, of course, our stratified model. But if we want to make sure that we also have sort of the typing for our stratified model, we have to do a little bit more work. So we consider the projection onto the first leg. So that's going to be this morphism. And then we're going to compose that with our typed SIR model, which represents this morphism, to get the complete typed stratified model. And again, we can use CATLAB and algebraic Julia will produce a visualization of our typed and stratified model. And so this diagram, again, it was produced by CATLAB and represents that stratified model. So finally, I'd like to bring it back to that motivating example where we stratified a bunch of different disease models by a bunch of different movement models to show that this really does automate the process that was done by hand in that paper. So again, for our disease model, consider our typed SIR model. For our movement model, this is the flux model where we have now 2 different places. People can move freely between places. People in place 1 can interact with each other, and people in place 2 can interact with each other. When we take the stratification, we get this sort of total stratified model. And if we apply the law of mass action to this Petri net, we recover almost exactly the dynamics that were derived by hand from that paper. So this is really an automated process of getting those models. We could consider changing our movement model now to the simple trip model. So here we have people who live in place 1 and are currently in place 1, people who live in place 1 but are currently in place 2. And of course, you can sort of move between where you currently are, but not between where you live. Now, if you're looking at this and you're like, wow, that seems really complicated, I definitely don't want to define that by hand, you are like me. And so what's actually really interesting about this particular movement model is it itself is a stratified model. It's the flux model, which we saw in the previous slide, stratified by a model of where people live. And so when we take sort of the stratification of our SIR model by the simple trip model, we actually have this sort of hierarchically stratified model where we have these three different pieces coming together to build this large Petri net. And again, when we apply the law of mass action, we recover almost exactly the dynamics that were derived by hand in that paper. And finally, just for one more example, we could change our disease model to something like the SIS model. Again, take the pullback. And then if we apply the law of mass action, again, we get the dynamics that correspond to the ones derived by hand in that paper. And so by automating this process, we really made it scalable so that if you want to add a new disease model or a new movement model, the process is really smooth to extend and to test new types of models. Anyway, thank you so much. I'd like to acknowledge the whole Algebraic Julia team, as well as John Baas for insights into pullbacks of Petri nets, and Sean Wu for bringing to our attention the motivating papers in the introduction. If you'd like to learn more about Algebraic Julia, you can check it out here. This work is also part of a longer paper called An Algebraic Framework for Structured Epidemic Modeling. And you can check out a Jupyter notebook that has sort of the complete demo with all of these different examples at this GitHub repo. So thank you so much.
Sophie is available and other collaborators are around in case someone wants to ask something. So let's thank Sophie again. Okay, now we have the coffee break. 25 minutes.
Great call, Sophie.
Technical kind of question. I did want to ask some questions after the talk. Is there like a Slack or something where you can do this?
There's in the email we sent, there's a link to a Zulu chat room.
Right. Okay. Since I didn't register in advance, I probably didn't get this.
I can probably. Did she drop off?
No.
Ross, do you have a question about? Do you have a question for Sophie?
Oh yeah, I did.
Oh, okay.
I was going to ask about rates.
Yeah.
Would you like to answer a question, Sophie? Or do you want to go to the coffee break?
I think this microphone is working.
Yeah. Or you can use this. But I should have planned this.
Oh, try to talk just into this one. Here?
Hello.
Hey.
Hey, Sophie, I really enjoyed the talk, and I think this work is extremely cool. So you had this interesting model where there was people could go into quarantine or not.
Mm-hmm.
And I would have expected that people who are not infected would do this less frequently than people who are.
Mm-hmm.
So I was wondering about rates. Do you have any way to do rates in this modeling at the moment?
I think the way it works in my mind is that they really should be specified afterwards when you have the stratified model. But I think sort of things like rate fitting is, I think part of fitting the model can be assigning rates sort of once you have the stratified model and comparing it to data.
Yeah, okay, that makes much more sense to do it when you have the full model.
Mm-hmm.
Yeah, thanks.
Yeah. There's also the actually, I should probably say it to the microphone. Yeah, we also have the default adjunct product will like tuple the rates. So it'll
I'm one of them.
then you have to like pick a commutative monoid to
I
collapse that back into a single
Oh,
number.
yeah. So regarding,
But you can at least get like the tuple of
I wasn't able to
if
pay
you wanna do
yesterday.
that.
Right. Is there any chance I
And
can?
that's a good, Chris Brown's talk today, or
Bruno, okay.
tomorrow,
I'll
we'll
just
talk
use
about
that.
that. He's got kind of that he
So question on here.
starts
She was
here
the
and
host
finishes
at
the
the first
parameter
session
estimation.
yesterday. Was
Of
that
like, how do you connect these models to data? And he uses this like, when you multiply models, you tuple the weights.
Okay, yeah,
As
I'll-
an
I'll
initial
just-
guess for what that's part of this optimization.
Okay, I look forward to seeing more of that tomorrow.
Great, yeah. Thanks, Sophie. Great talk.
Thanks, Toby.
We're going to coffee.
Hi, is it possible for one of the organizers to start some breakout rooms so the online people can actually talk with each other during the break? That would be awesome.
How many should we create then? Okay, yeah, we will try to do that. Choose rooms and choose. Maybe a bit more like 4. Hopefully you can join now. We created 4 rooms, so you can join.
Thank you.
So there's one with, so the second one we don't know.
Sweet. Hey, the clicker doesn't work.
Oh, yeah.
Is there like a button or something? Nope. There we go. Sweet.
Magic. I don't know how it works. Just
Oh, testing. Is it not working at all, or is it just dim?
hello.
Hello, hello. I may take the mask off once people are settled, but
No idea what's going on. Let's try do mine. I'm gonna do the classic move.
turn it off and turn it.
Okay. Test. Try to speak.
Hello, testing. 1, 2, 3.
Anything? Try to bring it closer, maybe here.
Testing, testing. Oh, okay.
I feel like on the color.
Testing. Okay. That's good. So is that a 20 minutes including questions?
It's 20 minutes including questions.
Oh, okay. So I'll try to leave time.
Are we tapping to the right thing? Are we tapping to the right thing?
Before you mute. You're not muted. Sorry, before you remove that. Hi, everyone. I'm just going to make a quick announcement that only concerns people in person, so we're going to mute for 30 seconds.
Oh, sorry.
And there. And
After you hide the meeting controls, you have to alt tab it into the right window, otherwise it won't work.
Okay. Sweet.
Okay, so we're ready to start our second session for the day. And we're going to start with Brandon Shapiro. He's going to tell us about dynamic operads for evolving organizations.
Right. Thank you so much. And thank you to all the organizers and everybody for coming. This is a really cool conference. So, like you said, the idea here is to combine dynamic structure, which we're going to describe using polynomial functors, with operatic structure that's going to give it a bit more of an algebraic flavor and describe a sort of self-similar nesting structure that we think is really interesting. So the outline is basically to describe how we can talk about diagrams like this, where we have these different components that wire together, and we're able to look at them inside these sort of nested boxes, as you see in this picture, but also where we have dynamics, meaning that these wirings are changing in a way that is coherent with that nesting. And then at the end, I'll talk about also one of our applications, which is to describe a evolving prediction market. We also have applications in deep learning and are pursuing more and welcome any suggestions or connections that people have. So I'll start by getting a lot more specific about that. But before then, I want to talk a little bit about the motivation behind why we started thinking about these things and how we sort of see these ideas applying very broadly to the world in addition to mathematics. So I'll tell you a little story. I work at the Topos Institute now. In 2021, that was not the case. So there was Topos Institute, which includes more people than just Tish, David, and Brendan, but that's a few of them. And they were wired together in some way that may or may not look like this, probably not. And then here was me off in the middle of nowhere, quite literally, in fact. And then in 2022, a couple of things happened, or leading into 2022. So Topos, if you just look at the Topos box, something changed in there in that their wiring changed. It opened up in a sense. And now there was sort of a new input that Topos could take and a new kind of output that Topos could give. And that happened all within the Topos box, but then also in the rest of the world. Another thing happened, which was that, my wires, not only did Topos open up its wires to new input and output, but also those wires ended up connecting up with me, which has been great fun. And this is a pretty good explanation of like what we're trying to model here, where we have things that can change inside of one box and things that can change on the outside of a box. And those are gonna be coherent with what would change if we didn't even look at the box. Like why is there a box around Tish, David, and Brendan? And then over here, I'm wired into that, but in order for the box to remain the same, I'm not inside of there, but maybe I should be. Maybe now it would be better to relabel the boxes so that now Topos includes me. And so we haven't really solved how to model all of these very vague ideas that I just described, but this project is sort of an attempt to start doing that. So relabeling and moving people inside and out of boxes is not quite something we've accomplished yet, but the nesting structure and the dynamics we have a lot more to say about now. And maybe this convinces you that ideas like that could describe more than just the more numerical examples of like prediction markets or deep learning that that I've mentioned already today. So for a bit more of math, we have these wiring diagrams, and I hope to convince you that these correspond in a meaningful way to polynomials or polynomial functors. I'm just going to say polynomial for the most part. And I'm going to say polynomial because that's really what they look like. So you'll remember these from Toby's talk. It's the same notation, I believe. These are just like classical polynomials, except the coefficients are sets rather than like real numbers. And the exponents are also sets. And so I've given a few examples here. And we also have, you can do a lot of the usual things. You can add them together. So I guess these are all monomials, which is more convenient for the pictures today, but you can have sums of these things. You can take products of them in the usual way. And then you have this other cool operation called the tensor or the Dirichlet tensor. And this is not the same as taking just like the usual product, multiplied product of polynomials, because in that case, you would still multiply the coefficients, but you would add the exponents. And that's actually not what I'm interested in for today. We multiply the exponents instead. And in a minute, maybe you'll see why. So we also have this idea of morphisms between polynomials, which classical algebra doesn't really give us, though it arises pretty naturally, even though I'm not going to get into that today. So just in this example, I'm trying to go from P tensor Q into R. And the first part of one of these morphisms is just sort of what you would expect in the sense of a forward pointing map between the coefficients of P tensor Q, that's this C, D, E, and F, into the coefficients of R, which is F, G. That part seems reasonable, and then it gets weirder in this other part where we have an A, which comes from the exponent of R, the codomain. And then we again have the coefficients in the domain. And from there, we're going to A, B, C, and those are the exponents of the domain. So the second part goes backwards. And this is exactly what Toby described in more generality in his talk. But this may seem kind of random. Like, why would I write it this way? This is just arrows between a bunch of letters. And the idea is that we want to think about these graphically. So we want these morphisms, we want to think of these morphisms as wiring diagrams, where the exponents are the inputs. So down here, we have P and Q. So tensor in the diagram is just sort of putting things next to each other. And then they have inputs corresponding to their exponents. P has A and B, Q has C. They have outputs that are their coefficients. P has an output of type C, output of type D, Q has E and F. And then we think of R, the codomain of this polynomial morphism, as the outer box. And then from this perspective, these functions make a lot more sense because we come in to sort of the interior of this box that's outside P and Q. We come into that from the inputs to R, it's just A, and the outputs of P and Q. And then these functions just say, okay, well, we need to be able to wire those things into the inputs to P and Q. That's this A, B, C, as well as the outputs of R. That's F and G. And so in this case, in order to make things a little more general, I chose sometimes you just take the identity. We have an A here. We need to give an A here. That's this line. Sometimes I'll ask you to provide a function. So here we start with D and we end up in G. So that would be like a function from D to G. And these pictures aren't necessarily the most general examples of these functions, but they're ones that often come up in practice and are a really nice visualization tool. So the next thing I want to talk about is the dynamics side of things, where, so we have this general definition of a coalgebra for a polynomial, like what Toby described, but I'm only going to really be focused on a particular instance of this, where we have a set S of states. And the idea is that this coalgebra structure is going to tell us how we change our state based on some kind of input. And in this case, what we want is the states to describe one of these wirings. This wiring is a state of our system. And it's going to change based on what is flowing along the wires. And so the way we model that is using this internal Hom polynomial that Toby talked about, and which I'm just going to describe in this sort of narrow case of a monomial. It has a much more general form. But for this purpose, the idea is that its coefficients are just these morphisms of polynomials from P tensor Q to R, these wirings. And then we have to choose what the exponents should be, and we pick this A, C, D, E, F. And those are exactly the things that I mentioned before as coming into the sort of wiring portion of the diagram. The input to R and the outputs of P tensor Q. And from them, given one of these morphisms, you can derive everything else on the wires. You get, the element of G and B, and if there were more, you can sort of push those things around the wiring diagram, and that tells you all of the information. And so here it gets more specific. A coalgebra for this, if you sort of unwind what happens when you plug in S for Y, Y is our variable, just like a polynomial is classically a function on the real numbers. Here it's a functor on the category of sets, where we interpret these things as products and exponents in the usual way. And so when you're mapping from S into this, you need both a function from P tensor Q to R. And so that's how one of these states encodes a given wiring. And then you also need to know how you're going to update that state. And so this function from ACDEF to S is saying that, okay, we're in a particular state, we have a particular wiring, we know what is flowing on the wires, what elements of these sets, A, C, D, E, F, and all the others are on the wires, and then we're going to move to a new state based on that. And then the last piece of the puzzle, which is the main new contribution in David and my paper, is to incorporate operads into this. So with operads, so here's a sort of very basic definition of an operad, which also satisfies some equations. The idea is that it's n-ary operations which compose in a certain way. If you haven't seen this before, I'll put up a picture in a minute that will hopefully make it more clear. But what we're interested in is dynamic operads, where each of these sets of n-ary operations are also the states of a coalgebra from P tensor n to P in a compatible way. So what does that mean? So now we're back at this nesting diagram, and we want to think of all of the boxes as interfaces described by a fixed polynomial P. So in this case, it looks like P has two inputs and two outputs, though of course that's an arbitrary choice. And when we have this sort of nesting diagram, you can be in a state on the outside. So it's a state, and it comes equipped with a particular wiring according to this coalgebra structure. So here this would be an S2, and that's going to be a P tensor P to P coalgebra. That's why we have two boxes. And then we also have these states on the inside. And so being an operad means that when we have that we can plug in, we have this two-ary operation, binary operation, we can plug in these two other operations into each of the boxes for it, and that gives us a new operation when you forget the boxes. And this playing nicely with the coalgebra maps means that when we do this, when we forget the boxes, we also have these states, these explicit choices of wirings for each state on both the insides of the boxes and the outside. And so when we forget the boxes, we get a new state. We want the wiring, the action of that state, to be precisely this, just the wiring diagram you get by forgetting those boxes. And you can write out a formula for how those functions compose in this operatic way. And you also want the updates to agree. So this is sort of what I was talking about at the beginning with the topos story. In here, based on what's flowing along these wires, the inside box on the left is going to update its state, the box on the right is going to update its state, and the box on the outside is going to update its state. And then in those new states, you can compose again. And you want that to be the same as just forgetting the boxes in the first place and then updating this whole system. And so we thought this was a particularly nice kind of structure, and I won't get to it today, but in the paper, it also involves a neat sort of enrichment of lots of different categorical structures, but including multi-categories, and in this case, operads, in a monoidal double category of these coalgebras. But I won't say anything more about that right now. I'll just finish by mentioning an example where the idea is that we want a system that can take a bunch of different people making predictions about which output from a finite set X is going to occur. And we want it to be able to aggregate them in a way that maybe prioritizes some over others. It trusts some of the predictors more than the others. And so we build this polynomial where you have sort of a prediction for the likelihoods of each outcome. And then the input is, well, what is the actual outcome? And then again, when you take this n-ary tensor product, you just product both of those by n times. And then our states are these distributions of how much we trust each of the n people making predictions. And we want those trusts and the probabilities of each outcome to not be zero. That's mostly a convenience, though there are some more intuitive explanations for why that would make sense. And that's an operad, for one thing, because you can take, given a distribution of distributions, you get a new distribution by convex combination. And then we want to think of these states as having actions kind of like this. So you get an input, which is, well, what event actually happens? And you just sort of copy that and send it to all of the players. And then they've all made their predictions and you've aggregated them using this trust distribution sigma. And that gives you your new one. And you can nest this as well. This is a nice about Operad structure. You can combine a bunch of players into one group and then treat that group like a new player and combine it with other ones. And all of this is consistent with not just this action that I've described, at least in pictures, but also this update where whenever an event happens, you update your trust based on how well each of them did. So if they rated this tau I of x, if they rated the actual event that occurred very highly, their trust will go up relative to the others after we normalize. And if they didn't rate it very highly, their trust will go down, and this evolves over time. And while I'm not going to prove it to you here, you can see in the paper that this does respect the operatic structure. Great. Well, I'm just about done. Thank you. So that's actually all I wanted to say today. In fact, I'll just mention that this is all based on a paper by David and I that can be found here on Archive and at ACT. And we're very interested in hearing, thoughts, ideas, examples that people might have about this or any sort of related ideas. Thanks so much.
So we only have time for one question.
I see the first half of this as you could use this to model deep learning and the learning process. But have you considered using the second half to model improving deep learning models? Once you train certain models, people like to combine them. And they usually average or take majority vote based on what models say. This seems really cool to me because once you've deployed the deep learning model, you could actually start to tune which models you trust the most.
No, we haven't, but it sounds like we really should. I'd love to talk about that more. We definitely use this operatic structure to sort of to describe these like nested learners. I hope I'm saying that right. But I hadn't thought about using this to compare them. That's a really cool idea. Thank you.
Okay, great. So let's thank Brendan again. The next one is online.
Hello. Hi.
Yeah. Very sensitive.
Okay. I don't know how to share the screen. It's disabled. Sorry? I don't have permissions to share the screen.
Please wait. We're doing it right now.
Okay.
Make call. Okay, you should have permission now.
Yes. Right, hello to everybody. My name is Andrea Censi. And this talk is about negative information. So the first negative information I have is that my co-authors, Jonathan Lorand and Gioele Zardini, were supposed to be there in person, but we actually got a double COVID combo. So it's just me and remotely. First, I will talk about what is negative information, why do we care? And as I will give as an example, infeasibility results in robot machine planning. We found this idea of negative information present in many applications where the positive information is a morphism. So we asked the question, okay, what would be the corresponding categorical notion for negative information? The idea is that we're going to represent negative information by negative arrows, which we call norphism, as opposed to morphism that carry the positive information. So we're going to define a category as a category that has some more structure for thinking about this norphism, including a notion of compatibility between morphism and norphism, so that we can talk about coherence. Now, interestingly, we'll see that norphism don't compose like morphism. So as you know, given two compatible morphisms, you obtain the composition. However, norphism need a morphism as a catalyst. So we have two operations that compose morphism with norphism to obtain a norphism. So this is all very weird. So at some point we thought, okay, is this just a mess that we are creating? And in fact, the answer is no, because we can show that we can recover these weird rules using a rich category theory. And what I'm going to show you is that just like if you have a category reached in a set with product, which we call P for positive, then you can derive the data for a small category. Then we will define a category Pn such that a Pn enriched category gives the data for a coherent sum category. So the conclusion will be that morphism and norphism are the same substance, and norphisms provide a way to categorify the negative information. One notice that we recently updated the paper, but it's not up yet. So please wait a couple of days before you look at it if you're interested. Here's a motivating example. In robotics, we think about robot machine planning, which you need to move a robot. So we need to find an optimal path between two robot configurations. And this path should avoid obstacles and have a minimal cost. And the cost could be the fuel required or the minimum time it takes. So think of this as a quasi-metric space. So you have a cost to go from one point to another, and you can concatenate cost. However, it's not symmetric, right? Because it could be different costs to go from A to B than B to A. So this is very nice to define a category. So you have a category in which the objects are points in some free space, and the morphisms are the paths in the space that have an additional cost associated to them. When you do composition, you concatenate the paths and you sum the cost. Now, when you think about algorithms, you find the following. So a complete algorithm is something that can find a path if it exists. Or if it doesn't exist, it gives you a certificate of infeasibility, which means it proves to you that it cannot exist. So the path is positive information and it's a morphism. The negative information, the question is, what is that categorically? Or also, optimal algorithms are those that provide an optimal solution, which is a pair of a feasible path, which is positive, which is a morphism, plus a certificate of optimality that says there is no better path. So this is negative information. And again, we ask, what is this categorically? And in some cases, negative information actually is a first-class citizen, like heuristics used in A star. To build the intuition, consider the case of thin categories. So in a thin category, there's at most one morphism per set. So these are preorders. So it's just like motion planning, only with connectivity. And we postulate these semantics. If there is a norphism from X to Y, and we use red and dashed arrows, then we say that there is no morphism from X to Y. Vice versa, if there is a morphism from X to Y, there cannot be any norphism from X to Y. So in this case, they are exclusive. And when we think about this in terms of axioms, we see that the norphism rules are the opposite, the dual to the morphism rules, right? So we know that there's a morphism from X to X, Instead, we know that if there cannot be a morphism from X to X, because there is also already a morphism, so it gives a contradiction. And this one is interesting. It's the opposite of this. It's the opposite of the first one. So think about this. So if there is no path from X to Z, it means that for every object, the path must be interrupted either between X and Y or Y to Z. So this one is non-constructive, but I'll give you a constructive version now. So if we revisit that constructively, we have two composition rules. So think about this. So here we know that we cannot go from X to Z because we know an morphism N, but we can go from X to Y because there's a morphism F. So this implies that we cannot go from Y to Z because otherwise we could go from X to Z. So it's just like we have a generated morphism that we call F composed with N. So in this case, morphism and morphism are the same source. In the case of the same target, it is similar. So if we know that we cannot go from this to this, but we can go from Y to Z, then we know we cannot go from X to Y. And so we obtain naturally these two rules for composition in which we use morphism as catalyst. So there cannot be a morphism plus morphism composition rule because if you think about it, it doesn't make sense. So there is no category of morphism. Morphism are complementary to morphism. Now, here's a more general definition. We define a category as a small category, so with all the usual structure, plus we define for each X and Y a set of morphisms. So we use nom instead of hom. And we write n dashed arrow to say that n is a morphism. Plus, we define a compatibility relation between the two sets. So on for each pair of objects, we have hom, we have nom, and we have a relation that tells which morphism are compatible with which morphism. Now we can generalize the usual notion. So a subcategory is just like it's a subcategory with a selection of morphism. And then we can define a coherent subcategory, which means that the morphism and the morphism that you have chosen to define the subcategory are compatible. So this is a generalization of subcategories in the sense that they are a generalization of what is a coherent view. A subcategory is a coherent view because it's close to composition. A subcategory is coherent because all the morphisms are compatible with the morphism. So this allows to distinguish between absence of evidence. For example, an empty subcategory is absence of evidence versus an evidence of absence. So you don't have any morphism, but you also have enough morphisms to rule out all the morphisms. Now, there's a constructions that for which you can obtain these composition operators. Before we've done that, these interpreted in a thin category, but you can go through you can define this more generally. So the construction goes like this. Suppose that you have an F and an N. So now this blue box is the morphism, this red box is the morphism. Then you can think of the morphisms that are incompatible with the morphism. So those are excluded. But because we have F, then that allow you to jump from this set to this set, then you can think of pulling back the incompatible morphism and say, look, all these morphisms are also violated because I could compose with them with F and obtain a forbidden one. And so in the end, you can obtain a set of forbidden morphism that define this morphism in this nom set. And in this way, you have found this rule. The other rule is symmetric. So here's an example. We define a category Berg for hiking on the Swiss mountain. So think of a manifold. Actually think about, so as a category, the objects are elements of the tangent bundle. And the morphism are the paths on the tangent bundle. So there's a velocity at each point, and there's a steepness. So because we are not, as a human, you only can traverse paths with the bounded steepness. So that is this sigma that tells us which paths are traversable. Now, what could be a morphism here? So the morphism is a path. A morphism, we take it to be a number, non-negative number, union infinity, which is take to be a lower bound on the path length. So now the compatibility condition is that f a path is compatible with a morphism if the length of the path is greater than the lower bound given by the morphism. And now we can define an optimal path as a pair of a morphism and a morphism. So if you know a morphism from X to Y, and you know a morphism from X to Y, which is equal to the length of F, then you can say that F is optimal. Now you can easily think about composition. So if you know that you can go from Z to Y, but you know that going from X to Y takes N, then going from X to Z takes a minimum N minus the length of F. Then we can think about how to generate the morphism, right? There could be axiom schemas. For example, you know that for every pair of points, the path will not be lower than the distance as the crow flies, right? You also know that the path cannot be lower than the geodesic distance on the manifold. So that's another schema for creating morphism. And also you can derive bounds due to the inclination bounds. Now, I showed you what are morphisms. I'll give you an example. There are more examples in the paper. Now, in the second part, I want to show you how we can use a rich category theory to derive these notions. So this is one standard definition of enrichment. So I remind you that given a monadal category V, the definition of a V-rich category E is a tuple, where you have a set of objects and functions A, B, and gamma. So A gives you for every pair of objects an object of V. Beta gives you for every triple of objects a morphism of V with this signature. And gamma gives you for each object a morphism from the unit in the monadal category to alpha of XX. And very importantly, you want to these diagrams to be satisfied. Now I will define the category Pn that we're going to use as enrichment. So this is kind of technical, but I'll give you the intuition first. The objects in the morphism are dependent pairs that have a positive and a negative part. Now, the positive part is a copy of P, which we define as the set with products, okay? So there's a copy of P inside there. And then there's a negative part, which is intertwined with P. So it cannot really be factorized. However, just for intuition, you can think about N0 defined as set up with plus, and but instead of having just being the product of P with N0, there is N, which is a dependent version of N0. So I read the definition. The objects are a pair where H is a set and M is a function that goes from H to the power set of another set N. Now, a morphism is a pair of functions. So the positive part, again, is a copy of set with products. So just a morphism from H1 to H2. Phi is a dependent version of set up. So it's a function that goes from M2 to the result of M2 to the result of M1. But these sets are dependent on the first component. And also, when you think about composition, the positive part composes as in set, the negative part composes in the opposite direction. And again, if all these functions were constant, then this would be set up. So it would be just composition of the opposite. Now, a reviewer asked if Pn is some another category of poly. The answer is that I don't know, and probably maybe with some little changes. And I'm in the process of becoming polyamorous, so I hope to discover soon. Or if somebody wants to help, that's very welcome. So now I define a monadal structure on Pn. So first, I define this composition on the negative part. So given two functions M and M2, I define the composition as something that takes the arguments for both, evaluates them, and takes the union. And this is the definition of the monadal structure on Pn. Again, like squinting a little bit, there is the left part, which is as in set with products. The right part has this composition. You could see here, again, I show you that if these functions C, F, Psi, G were constant, this would be just the sum of two sets. So that the sums of two functions. So that would be set up, but it's not because it's dependent. Now, I want to show you that enrichment in PN describes coherence of categories. Now, let me remind you of the traditional construction that if you have a category reached in P, where P is set with products, you can define a small category. So this is one direction. So if you're given this tuple, then you can define the objects of C to be objects of E. You can use alpha to define the omsets. You can use beta to find a function that has the same signature as composition of morphisms that you need. And then you look at the diagrams, and the diagrams imply that this function is associative. So you use it to define the composition. Then you use gamma, you relate it to and find that it selects a morphism for each object. And the diagram's constraints imply that this is unital with respect to the composition. And so that is, you define that to be the identity. So in the paper, we wrote proof, which is analogous. So just like enrichment in P gives you a small category, a category reached in Pn gives you the data to specify a coherent subcategory. And the sketch is that, well, the P part, which is in there still, recovers this construction, right? While the N part recovers the category structure. You get nomsets, you get the compatibility relation, and you get Northwest composition. I will not show you the full proof here, but I want to show you one highlight. So in the at some point in the proof, we define the yes.
Just a few more minutes.
Yes, thank you. I have just another slide. We define function I, which gives for each morphism the incompatible morphism. And we can construct this dependent function given the data in the PN rich category, which has this signature. And now what's interesting is that if you take the proposition as types interpretation, then you can recover from this the logic for morphism. So I don't expect you to follow, but I want to give you the sketch. So this function from every FNG means for all FNG that are compatible, you look at this set that tells you whether there is a morphism for this morphism. So if this is empty, then it means that this composition is allowed. If it's not empty, then the composition is not allowed. The elements of I evaluated there are the morphisms that contradict the morphism. So now you can pick for each of them, for each morphism n, you can evaluate the function that you have, and you obtain a function here. Now, if you know that f is allowed, so that this is empty, so you're going to end up in this union in this part. So if f is empty, so if f is allowed, then you obtain a negation of G. So if the composition is not allowed, then either one or both are not allowed. Now, if you look at this function that you obtain a function given an f and an n, gives another morphism. So this is the first type of composition. And if you go the other direction, you obtain the second composition. So these weird rules actually come up from enrichment. Now, conclusions. What we showed is that negative information can be categorified using these negative arrows, as opposed to using some logic on top of category theory. Morphism are different than morphism. To compose, they need morphism as catalyst. Now, categories generalize categories to account for this morphism. Querying some categories generalize subcategories to express a coherent set of information of a set of morphisms and morphisms that don't contradict each other. And we show that this is can be derived using rich category theory. Just like you find that a category is defined by a set of rich category, a PN rich category gives you a coherent subcategory. For future work, we want to survey natural morphism structures in the wild. I think there's a lot of things to do by reinterpreting a lot of algorithms into producing positive and negative information. There's this question whether PN, what's the relation of PN and poly, which we're going to think about. And finally, generalization to higher level concept. Now we have defined morphism. What would a functor be, like a functor that is negative? And so there's a lot of work to do there. Thanks for your attention.
Hi, thanks. Great talk. I was wondering, it seems like there's sort of an asymmetry where the morphisms are the morphisms aren't. So I'm wondering if you have any thoughts on why that is. Like maybe you could have morphisms being dependent on the morphisms.
Ah, right. That's an interesting thought. So if I understand, so the comment is that there's not a symmetry. There's more like a complementarity. Yeah, I don't know. Maybe you get something which is even more interesting.
Okay, great. So let's thank Andrea again.
Thank you.
There. Okay, not hear you yet. Okay, in a moment we'll hear Dragan tell us about Ramsey theory, category theory.
Oh, okay.
We can hear you.
Hi. Hello, my name is Dragan Masulovic, and I'd like to use the first few minutes of this talk to briefly introduce myself. I'm not a category theorist. I come from discrete mathematics, but in the past, let's say, 7 years, I've been interested in applying category theory to understanding phenomena in structural Ramsey theory. So the motivation is briefly sketched on this slide. The idea is that we can use duality principle to understand the dual Ramsey phenomena, which are pretty hard to understand. And if you've had any course in structural Ramsey theory or Ramsey theory in your undergraduate or graduate studies, you would see many direct Ramsey phenomena and not so many dual Ramsey phenomena. And also, category theory enables us to prove some piggyback proof strategies so that we can simply produce new Ramsey results, starting from all results and using some categorical juggling. But I will not speak about that today, maybe next time. So today, actually, I would like to speak about a phenomenon that I've just stumbled upon by working in this, let's say, categorical understanding of structural Ramsey theory. And I believe that this audience is the perfect audience to somehow to get some feedback from. Yeah, so I would appreciate any kind of feedback from you. It's about entropy, actually. You can use some combinatorial phenomena to produce an entropy function which is applicable to various combinatorial structures. And it's just a phenomenon which I would really like to share with you. Okay, let's go through a very simple example just to motivate what I'm going to speak about. So starting from the fact that entropy is somehow a measure of surprise, let's go through some very simple graphs. Now, this is an empty graph on 5 vertices, and if you ask someone who's had any basic training in graph theory how surprising this graph is, the answer would probably be not at all. Let's consider another very easy graph, and this one is also not very surprising. But now that when I've used these two examples, anything I display now will be somewhat surprising, right? So this graph is somewhat surprising. Now we would like to measure the amount of surprise by actually looking at the size of the automorphism group of graphs and comparing it to the size of the full symmetry group, right? So the sizes of the automorphism groups are obvious. And then I'll just compute the logarithm of the quotient of the size of the full symmetry group and the automorphism group of the graph. And here, for the first example, you just see that, see here, sorry, Here, for this graph, you'll just see this quotient is 1 and the logarithm is 0. The same holds for the second graph. However, in the last case, we get something non-zero. All right. So this graph bears some amount of surprise, much more than the previous two. All right. Now, let's consider another very famous class of finite structures, finite posets, partially ordered sets. And if we start with this poset, how surprising is it? Well, probably not at all. Another non-surprising class of posets are linearly ordered partial sets. They're also not surprising. And anything that I will display now will be somewhat surprising, right? Who could have expected that I would start with, rabbit ears? So if we compute the automorphism groups again, now we see that something interesting happens. This time, the more surprising graph has more automorphisms than the less surprising graph. So in this case, comparing the size of the automorphism group to the size of the full symmetry group will simply not be somehow indicative enough. However, there is another numerical parameter which is interesting in case of partially ordered sets, and it's the number of linear extensions. So this graph has 5 factorial automorphisms and the same amount of linear extensions. You can extend this non-existent partial order in 5 factorial ways to a linear order. And then, so this quotient is 1 and the logarithm is 0. In this case, for totally ordered graph, we have only one linear expansion. So there is only one linear expansion and only one automorphism. So the logarithm is again 0. Okay. However, this time for the third example, there is a certain amount of linear expansions, and when you compute the logarithm of the quotient, you get something non-zero. So those who are familiar with the recent development of structural Ramsey theory will immediately recognize these numbers, these expressions, to be small structural Ramsey degrees of graphs in the first case and partially ordered sets in the second case. So somehow one might come to the conclusion, okay, if I want to compute the amount of surprise or the entropy, let's just take the logarithm. This funny symbol, T tilde, is the small structural Ramsey degree of a particular structure. So let's just take the degree, the structural Ramsey degree, compute the logarithm, and let's hope that this behaves as an entropy. Unfortunately, this is not the case. We expect our entropy functions to have certain properties, and this one simply is not related to any property that would somehow look like continuity. Okay. So what are the expectations for the entropy function? So we would like our entropy function first to be somehow bounded by the logarithm of some diversity measure, whatever that might be in the particular case. And of course, we would like our isomorphic structures to have the same entropy, that the entropy of a structure is 0 if and only if it's somehow simple. And now we would like our entropy functions to be continuous. However, in this setting, so I would like to build an entropy function for arbitrary categories. So somehow the best we can hope for is actually to get our functions to be monotonous with respect to some natural ordering. And finally, we would like the entropy function to have the logarithmic property. Okay, so these are the expectations for the entropy function. And now I would like to go into technicalities just slightly to give you the notion of what structural Ramsey theory is about and how do we actually come to the notion of Ramsey degrees. And then I'll get back to just give you, to propose a categorical version of all that and prove several results. So structural Ramsey theory is a deep structural property developed in the 70s by Erdős, Graham, Leib, Rothschild, Gödel, Neshatril, and many other famous names in discrete mathematics. And the definition is straightforward. A class of finite first-order structures has the Ramsey property if for every A and B, for all structures A and B in the class, and a number of colors K, there is always a structure C in the class such that C arrows B, A, and K. This is the Erdős-Rada arrow, which has the following meaning. So if A, B, and C are some finite first order structures like graphs, partial ordered sets, whatever, this arrow notation means that no matter how we color copies of A in C with K colors, so we are now copying substructures, not points. So take a structure C, identify all copies, all substructures of C isomorphic to A, and attach labels to each substructure. So no matter how we color copies of A in C with K colors, there is always a monochromatic copy of B in C. That's the arrow notation. So basically, the Ramsey property tells you that for every A and B in a class, there should be a C, usually a huge finite structure, such that this holds C arrows B, A, and K. Meaning that no matter how we color copies of A in C, there will always be a monochromatic copy of B in C. All right. And then came the great surprise. When this notion was introduced in the 70s, it turned out that no combinatorially interesting class of structures has the Ramsey property. Right? That was somehow an unpleasant surprise. Fortunately, the situation was very quickly fixed. Already in the 70s, the idea was to simply add more structure. For example, consider ordered finite graphs with an extra linear order. And in the 90s, 20 years later, another notion was proposed. So this first point of view is nowadays referred to as the existence of precompact Ramsey expansions, which was introduced and studied deeply in the 21st century, actually. And another notion which comes from the late 90s is to simply relax the Ramsey property, and this leads to the notion of Ramsey degrees, right? It was proven a couple of years ago already that the two notions are actually equivalent, right? So it doesn't matter whether you add more structure, add linear orders, or relax the Ramsey property and go for degrees. Is the same thing. A class of structures will be Ramsey according to the first point of view, if and only if it's Ramsey according to the second point of view. So, all right. So relaxing the property means the following: that for every object A, there is an integer t which depends only on A. So t depends on A only, such that no matter how we color copies of A and C with K colors for any K, there is always a copy of B which is no longer monochromatic, but such that at most T copies appear inside. So it's not a monochromatic copy. We are no longer searching for a monochromatic copy, but we are searching for an oligochromatic copy where the number of colors that may appear inside the copy are given in advance, depend only on A. The least such integer T is called the structure Ramsey degree of A because it depends only on A. And it was at the end of the 20th century that first structure Ramsey degrees were computed actually by Willem Fouché. And as you can see, it's still a rather intriguing field of research because, let's say, some structuring Ramsey degrees were computed in 2005. Okay. Now, as for the categorification of the notion, we simply have to first identify the sub-objects as, we think of morphisms as embeddings. Okay, that's the model that we have. So think of finite structures and embeddings, and then two embeddings point to the same sub-object if they differ by an automorphism, right? So we introduce this tilde relation that tells us that f and g basically point to the same sub-object, and then factor the Hom set by this relation and call this the set of sub-objects. And then the arrow notation is straightforward, as defined on the previous slide. We just color, it's the same thing. A small Ramsey degree is just the least integer t which can be placed in this arrow formalism, and then we say that C has the Ramsey, a category C has the Ramsey property if every object in C has degree 1. Okay, that's just the standard Ramsey theory. And now, how do we connect this Ramsey property to entropies? Actually, now you can compute Ramsey degrees in a rather convoluted way, but looking at some special partitions. So the existence of Ramsey degree implies the existence of relatively complicated partitions of subsets. And I will not go into the technicalities here. I'll just point quickly to this lemma, which tells us that a Ramsey degree of an object can be computed as the minimum size of an essential partition, whatever that is, and then take the supremum of all those minimum sizes, right? So that's that's an easy lemma which connects Ramsey degrees to some special partitions. And then the idea is to simply consider entropy functions on partitions. So an entropy function on partitions is just a function that takes partitions of X. X is a finite set. Everything is finite here. In categories, composites are finite. Everything that can be finite is finite. So it takes finite partitions to real numbers and has some reasonable properties for like every other entropy function. I mean, this is a typical entropy function on partitions, right? So the examples are the Boltzmann entropy function, which just takes the logarithm of the size of the number of blocks, or the Shannon entropy, which is just the negative sum of probability of a block multiplied by the log of the probability of the block. For each block in the partition, everything is finite once again. Then again, and then this gives us the following. We can then introduce a Ramsey entropy based on H. You just fix a partition, an entropy function of partitions, and let's introduce this. For each object, we can compute this. So this is reminiscent of the small Ramsey degree, except that now I apply an entropy function on lambda. If H is the Boltzmann entropy, I'll just call this the Ramsey Boltzmann entropy. The funny thing is that actually I can introduce this for any category. Just take any category whatsoever where composites are finite, and you can introduce this notion. In many cases, this will produce a trivial entropy like R of X is infinity most of the time. Intriguingly, actually, okay, not intriguing, so it's not surprisingly, we have the following result. If a category has finite Ramsey degrees, then it emits an entropy function based on an arbitrary entropy on partitions, right? And this entropy function behaves, sorry, my time is almost up, so I'll finish in in a minute, right? And then this entropy function has almost all the desirable properties. What we are not happy with is that it does not have the logarithmic property, and sort of sub-objects of Ramsey objects have the entropy 0, but the other way around is not usually the case. So the idea was then to take a look at the Boltzmann entropy on partitions. So sorry, Boltzmann entropy. And this one is actually interesting because it's the maximal Ramsey entropy on a category. And then we have that C admits a Ramsey Boltzmann entropy if and only if it has finite Ramsey degree. So there is a clear connection between Ramsey Boltzmann entropies and existence of finite Ramsey degrees. This entropy behaves nicely. So it's 0 on sub-objects of Ramsey objects, and it's multiplicative. And so basically, it's just an explanation of phenomena. So why would this be of any interest? So on the philosophical level, this might be interesting because it may give us a possibility to think about the Ramsey property in terms of information theory. So identifying a Ramsey property in a category can be a hard thing to do, can be a very pressing, hard thing to do. So maybe we can use some strategies from information theory to think about the Ramsey property, a very combinatorial property, which on the surface has nothing to do with probabilities in information theory. And basically, this is the main motivation for going in this direction. And this is why I wanted to address the audience and somehow hope for some feedback. Thank you very much.
get them. One thing, so I thought this was all rather interesting. So, thank you for your talk. One thing I noted about your set of 5 or so axioms for entropy is a couple of slides past, you point out that you get this inequality. So actually go forward a couple.
Once again, sorry.
You write at one point R of A, B is less than or equal to
yeah.
plus R of B. So I wonder if you considered the fact that the entropy is subadditive unless A and B are independent as random variables. You have some sort of partition that has common edges. This might in fact be what you want.
Yes, actually, but the problem here is that A and B are independent, right? So, sorry, I was speeding, so I was not very correct. So I was not very precise. On the left-hand side, you compute R in the product of categories. So A and B are treated independently. That's why I am dissatisfied with this point, with Ramsey entropy defined on for an arbitrary entropy function. Okay, so this here on the left-hand side is treated just as it's R of the pair computed in C cross C. So A and B treated independently, fully independently.
Right.
Okay. Sorry, I was speeding up, so yeah, I wanted to say many things in a short time, so I was not precise.
No, well, thank you.
Thank you.
Thank you very much for a very nice talk. One question, is there any sort of uniqueness result for these entropy functions?
Once again, sorry, is there
any sort of uniqueness result for these entropy functions, or that, or in some cases?
No, unfortunately, not that I was able to prove.
Okay, yeah, thank you.
Actually, there are many kinds of Ramsey degrees. This is just one that appears in the literature most prominently. And every Ramsey degree can produce some sort of entropy function. So there is actually a multitude of entropy functions that come from various kinds of Ramsey degrees on a category.
Great. So if there's no further questions, let's thank Dragan again.
Thank you.
Next, David Spivak will tell us about canon entropy and polynomial functions.
Hear me? Microphone working? Yeah. Oh, I can't do it anymore.
No.
Yep. Okay, thanks. And thanks to the organizers for putting this all together. So I'll be talking about polynomial functors and Shannon entropy. And so broadly, I mean, so we're here to learn from each other, but what is this process that we're going through as I talk to you or you talk to me? So some information sticks, maybe something from this will stick. What is that? How do we store information in our minds or in databases or in the world? And then how do we use that information to like move about the world? So I'm interested in that sort of thing. And I study how, like, I started out in applied category thinking about how knowledge is stored and transferred in databases, because I was thinking like, maybe we could think about ourselves in that way. And then I started thinking about how dynamical systems interact to adapt and learn, like in Brandon's talk, because we interact that way. And so, so I'm trying to think about how this is even possible. What kind of math would make, maybe this isn't that complicated. Maybe there's some way that you can think about
learning and things like that simply as though it emerges naturally, because somehow it seems that it does. So entropy has been put forth as an approach to intelligence and learning. So Prigogine said that life could be understood as a dissipative system, that we are kind of somehow spraying entropy into what we think of as not us. And then we pack negentropy or organization into what we think is us. And Daniel Polanyi's notion of empowerment or Cameron Freer's notion of causal entropic forces are both entropy-based approaches to intelligent behavior. So I thought it'd be important to understand what those are. But I seem to only understand things when I can understand, write them categorically. So I've been trying to understand what entropy really is, quote unquote. And Leinster and Baas-Fritz's conception of entropy is great and helps a lot, but I somehow want to connect it in with dynamical systems and databases, because those are the ways that I think about learning and storing information. And then in around January 2020, I fell in love with this category called poly that people have now started making fun of me because everything's poly, 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 but that's okay, I still love it. And so it's the reason I love it is because its applications subsume everything I'd done with categorical databases. As someone said earlier, the comonoids in poly are exactly categories, and the comodules are exactly co-presheaves and data migration functors. So the things I've been doing with data migration that you saw with atchets and things like that in the algebraic Julia stuff, that's all just the comonoids and comodules in poly. You don't have to do anything to get there. But also interacting dynamical systems that change how they interact based on how the wiring diagrams can change in time based on what's flowing. That's really how I got into poly, because I noticed that that gave a good language for that. But polynomial functors are also used in functional programming, type theory. Brandon's thesis was about higher category theory using polynomial monads. So it's really applicable, but it's also highly structured in that it has all limits and co-limits. It has coproducts and it has 3 orthogonal factorization systems, 2 monoidal closed structures, co-closures, et cetera, et cetera, et cetera. So its monoids are operads, what are called sigma-free operads, where you can move the things freely. And its comonoids are exactly categories. So if you want to see just a paper that's 9 pages of just formulas with no proofs, and anyone who wants to prove these things should, there's a paper on the archive about that. But today I'm going to tell you about how entropy looks from the poly point of view. And I just want to say that I did not accomplish connecting it with databases or dynamical systems. So in some sense, this is a failure so far, but at least I understand how entropy looks. So, and this extends some work, a paper that Tim Hosgood and I wrote last year. This one's just functorial, where that one was not. So I'll show how to think about objects in poly as empirical distributions. And I'll show that there are distributive monoidal functors from polynomial functors with Cartesian maps to set times set op. And that sends some polynomial to some kind of invariant, some pair of sets. And the point is that the Shannon entropy can be extracted from those pair of sets. So you start with a distribution, you extract just 2 sets from it in a distributive monoidal way. So a functor that preserves all the structure that you care about, tensor and plus, at least in this case. And then we're going to get properties of entropy from the distributive monoidality of that functor. Okay, so that's the plan. Give background on polynomial functors, just in case you missed it earlier today. Give this functor from polycart to set times set op and its relation to entropy, and then talk about some generalizations. So what is a polynomial? It's like y squared plus 3y plus 2. That's 3y to the 1, 2y to the 0. And you can think about polynomial as a bundle. That's kind of a classical way people think about polynomial functors. So there are 6. If you plug in 1 here, you get 1 plus 3 plus 2 is 6. And those are here. And I'm going to call those the outcomes. And then I often call them the positions, but I'll call them the outcomes today because of the probability point of view. And so every outcome has some number of draws. This one was drawn twice. This one was drawn once, 0, 0, because it's y squared plus 3y to the 1, 1, 1, 1, plus 2y to the 0. And so you could draw it this way also as a corolla for us. There are the 6. There are the 6 outcomes, and this one was drawn twice. This one was drawn once, and these were never drawn. And so, yeah, you can think of it as an empirical distribution where this one was 2/5 of the time was chosen. This one was 1/5, 1/5, and 1/5. So in terms of probability distributions, it's empirical in the sense that we have the actual data that generated the probability distribution. Okay, a morphism of polynomials is just a natural transformation. A polynomial is a kind of functor, and a morphism is just defined to be a natural transformation between them. So if this is the functor that takes a set and cubes it and adds 2 times the set, and this is some other functor of the same kind of thing, then you could draw them as these corolla forests. And a morphism would send every outcome of this kind to an outcome of this kind. Maybe 1 was sent to 1, 2 was sent to 1 for some reason, and 3 was sent to 4 for some reason. So that would be a morphism of a natural transformation between these two functors. But it doesn't just send the outcomes to the outcomes, it also interprets the draws. So if somebody said, oh, my outcome 1 is your outcome 1, then they'd have to say, well, I got 4 draws. Which ones were those? Oh, that was my first draw. Your second one was my first draw. Your third one was my third draw, etc. Maybe I said it backwards. So it's some kind of map like that. And what does that have to do with entropy? Well, it'll turn out we're not going to use all of these maps. We're going to use the Cartesian maps. It's Cartesian if these maps on draws are bijections. So if you wanted to count how many there are from here to here, you'd find there are 6 because you're required to send 1 to 1 and 2 and 3 to 3. And there's like 3 factorial ways to do this. That's just a sanity check in case you care. So we're going to be interested in 2 fundamental invariants of a polynomial. And from the bundle point of view, if you think about a bundle, what do people care about? They often care about the base of the bundle, and they care about the global sections of the bundle. So if you have a bundle E to B, then these would be the base B and the set of maps from B to E that are sections. In terms of polynomials, they're the polynomial maps from the identity to P and the polynomial maps from P to the identity. So this one's the base and this one's the global sections. And so in case you want to check your understanding, here's this polynomial as a bundle. This outcome was drawn 3 times, etc. The base of this has 4 elements, 4 outcomes, and the number of global sections is 18, 3 times 3 times 2 times 1. Okay, so these are the maps from this thing from Y to this thing and this thing to Y, and they're functorial in opposite directions. So you have this map from poly to set times set op that takes the base and the global sections. Now poly is distributive monoidal, which means that you can add 2 polynomials and you can tensor 2 polynomials, and these were talked about earlier in previous talks. In terms of bundles, it's really easy. You take your 2 bundles, you add up the total space, you add up the base space, that's going to be the coproduct in poly. You could also multiply the base, multiply the product, the total space, and that is not the product in poly, but it is a monoidal product in poly, called the Dirichlet. And these clearly distribute because basically when you tensor and then plus, you're just doing the same thing on the tops and bottoms, so you easily get this. And soon we'll see how the fundamental invariants that I talked about before, the base and global sections, respect these operations. But first, I need to get you a little further through poly. So you have polynomial functors can be, you can take their derivative. So there's just one variable. So we're going to write p dot for the derivative. And we're actually going to be more interested in p dot y. So it's just the usual derivative. So if you take y to the 4th, its derivative would be 4y cubed. And if you take p dot y, you'd get 4y to the 4th. Okay, we're just multiplying by y. Now, neither of these is functorial in poly, but they are functorial in polycart. So you can take a polynomial functor, take its derivative times y, and that's another polynomial functor. And if you have a Cartesian morphism, that will be preserved or functorial. And the last piece of theory we need is a bifibration from poly to set. So if you take any polynomial, you can take its base, p of 1, and that is a monoidal star bifibration in the sense of Schulman, but we don't need all that crazy. I mean, I like all that stuff, but we're not going to need all that today. All we need is that if you have a map of sets, A to B, and you have a polynomial P whose outcomes are A, and a polynomial Q whose outcomes are B, then there's some kind of a junction. There's an F upper star that takes your B-ish polynomial and gives you an A-ish polynomial, and an F lower star that takes your A-ish polynomial and gives you a B-ish polynomial, and they're given by these formulas. So you have these outcomes A and B, Q has outcomes B. You get this new polynomial that has outcomes A, but how many draws were there? Well, let's just go forward into B, check out how many draws Q had for that guy, and then call that the number of draws in A. And how do you go forward? This is the classic push forward of measures. So in Baas Fritz Lenster's paper, it's all about push forwards of measures. That's F lower star. So you have this polynomial with an empirical distribution over A, and you wanted an empirical distribution over B. So you say, well, my outcomes are now B, and I just add up all the A's that went there. I just add up their, I just lump them together. So that's F lower star. We're going to need that one. So now I'm going to tell you about the distributive monoidal functors and how that relates to entropy. So the first thing is that when you take a polynomial and take its derivative and multiply by y, it's distributive. And so, okay, that's what I'm going to try to show on this slide. So how does this relate to entropy? what we're going to do is we're going to extract these two sets from any polynomial, and that we're going to say that doing this is a good idea because it's distributive monoidal. And then at the very end, once we have these two sets, then we can just take the entropy from there as just the log of something. So we'll extract both extensive and intensive entropies. What does that have to do with? Okay, so let's start. So so we have P, and we take its derivative and multiply by Y, and that's distributive monoidal, meaning if you take the derivative of P plus Q, you get the derivative of P plus the derivative of Q. That's from calculus. And if you multiply by anything, that's also linear. Multiply 0 or a sum by Y, and that'll give you 0 or the sum. But it also, that's just saying that it preserves coproducts. It also preserves this tensor product through this kind of derivation. You take P dot Y, tensor Q dot Y, you write it out, you multiply things, as I said, the way tensor works, and you get the derivative of P tensor Q times Y. So that means that this giant structure here, this distributive monoidal category there, maps to itself by this derivative, and that's distributive monoidal. But the fundamental invariants are also distributive. If you take the base or global sections of a bundle, that is a distributive monoidal functor. But what is the distributive monoidal structure on set times set op? So set times set op is a category. It's got coproducts because set has coproducts and set has products. So set op has coproducts. And so if you take two sets, A and B, A1, B1, and you want to add it to A2, B2, you would take the coproduct in the first variable and the product in the second variable. That is what coproducts will be there. But it also has another symmetric monoidal structure, and that was apparently known to the people who do dialectica, so Valerio de Paiva and others, that like if you take two pairs of sets, you can multiply the A's, and you can do this kind of funny thing to the B's, and these two things, the coproducts and tensor there, distribute. And that just gives you a monoidal structure on set times set up that I think is kind of interesting. So the fundamental invariants as a pair preserve these two. In other words, like if we take this functor from poly to set times set up, when we see what happens with plus, well, on the base, it's the sum of the bases, and the global sections of a sum of polynomials. You take two distributions and you put them side, or two bundles and you put them side to side. You take the global sections, it's the product of the global sections. So they preserve plus, and they also preserve tensor, because P tensor Q, if you multiply two bundles, the base of it will be the base, and the global sections will be some kind of this exact structure here. So they preserve plus and tensor. And so we have polycart, we take the derivative times Y, we get a polynomial. We take the base and global sections, we get a set and a set up, and let's call that H. And the reason we're calling it H is because it extracts everything we're going to need to calculate the entropy. So preserving, and this is the slide with the theorem on it. So preserving plus and tensor is going to give us the properties of entropy that we'll get on a later slide. So the last step is just to take our pair of sets, assume they're finite, sorry. So we assume our polynomial is finite. And we're going to take the log of, we're just going to do some logarithmic stuff. So what does it do? I'll tell you what this has to do with entropy on the next slide, or maybe the one after that. But all I'm saying is that once we've done this work, we've extracted everything we need, and then we take the real number of people, we let the real number of people take it from there. So the theorem is that if P is a polynomial, and you consider it as a probability distribution, 1/5, 2/5, 2/5, whatever, and you take the Shannon entropy of it, then that Shannon entropy is this loggy thing applied to the pair of sets. So that's the point, that we've extracted everything we need to get that entropy. So I'm personally unfamiliar with thermodynamics. So the following is joint with a physicist named James Dama. We should think of Shannon entropy as an entropy density, apparently, not as like an extensive, but an intensive entropy. So the thermodynamics picture defines what they call a partition function for distributions. And for us, that would be A to the A over B. That would be the partition function. And then the extensive entropy would be the log of that. And the Shannon entropy is like a density. We take that extensive thing and we divide by how many outcomes or how many draws there were total. So here's a worked example. So let's say this one was drawn 4 times and each of these were drawn 1 time. You can calculate the entropy of 1/2, 1/8, 1/8, 1/8, 1/8, and get 2. So we know this thing's going to have entropy 2. You can calculate that normal way. We can also take its derivative and multiply by y. The derivative of this is 4y cubed, so multiplied by y is 4y to the fourth. Derivative of this is 4, so multiplied by y is 4y. And so we can take the base and get 8. That's the base of this thing. We can take the number of global sections, that's 4 to the 4. And then, so that would tell us that the partition function is 8 to the 8 over 4 to the 4. The extensive entropy is its log, and the Shannon entropy is that log divided by the number of draws, 8, or A. So we get 2. That's, yeah. The consequences of distributivity are that H preserves tensor, and the fact that it preserves tensor and properties of log immediately give us that the entropy of an independent pair of distributions is the sum of the entropies. And the fact that H preserves plus is more subtle, but we see it better in the extensive entropy and the partition function. So again, this is joint with James. If you write P as a sum, P is some polynomial or distribution, but you write it as the sum or coproduct of some simpler distributions, you know, A1, P1 through Pn, P1 through Pa, say, then that would be the same thing as given a function that tells you for every observation, sorry, for every outcome, which of the A lumps it's in. And then from this, we can kind of lump together those distributions. So we can push forward the measure. And so then it follows from the fact that H preserves sums. H preserves both, it's distributive, so it preserves tensor and sum. And we get the partition function of the push forward, or sorry, the original partition function is that of the push forward measure times the product of all the little pieces. Or in terms of extensive entropy, the entropy of the big thing is the entropy of the push forward plus the sum of all the little entropies. And so that's the usual chain rule for Shannon entropy follows from this. So just to summarize, entropy and poly are both, to me, amazing things, and they have, for some reason, overlapping applications. So entropy is well known throughout the scientific and technical world, and poly is the most highly structured category that I've ever seen. So both of these have applications, and the fact that they both have applications to interacting dynamical systems. I was hoping to see Huffman coding or some other thing that people actually use in real world come out of something like this investigation, but it didn't, at least not so far. But we at least have some interpretation of entropy in poly, namely objects in poly can be viewed as empirical distributions, and there's a distributive monoidal functor that from poly cart to set time set up. The theorem was that if we make A, B, be the out, like we apply this to some polynomial P, and we can get the Shannon entropy by some kind of log thing. And then, so it just comes from these two sets, and all the entropy relevant data of P is just encapsulated in those two sets. And again, somehow it still feels foreign to me, entropy does, even after all this, but I hope that having different sorts of categorifications will help clarify it, and that someday we'll figure out a way to bond it to dynamics and things like that. So thanks.
So are there any questions? Yeah.
Thank you for a great talk. So it seems like the details of your formalism are completely different from the approach of, say, Leinster or dynamic gravity, but the conclusions are very similar. Are you aware of any particular connections between your work and theirs?
Yeah, it is all the same in some sense, though they the reason the outcomes are the same is because we're just trying to recover things we already know about entropy, like the chain rule and stuff like that. The reason the formulations are different is because I'm constraining myself to, I must work within poly because all the things I've cared about in my research have been in poly. So if I can do things there, then maybe I can connect things together. And so I'm just trying to keep myself to a narrow box to see if I can still do it. And so the connections are just going to be that it's all kind of the same story with different packaging. And I think that's about it. Yeah.
Okay, anyone else? Yeah.
Hi, thanks for the call. Have you considered replacing set time settle with poly again? Or is there like a very good reason why you're looking at set time settle?
I think I wanted to say that these are two that I have almost, I wanted to think of them as like cardinalities or as numbers that I could just apply a numerical function to. So what I would need, I guess, is to think I mean, if I was allowed to use a poly, why not just use the identity functor and then take the entropy of the distribution? So somehow this is saying I pulled away so much that I just have you started with this distribution, now I just have two sets. And I did that in a way that preserved a lot of structure. And so I think that's, maybe I missed something, but yeah.
No, it's just
yeah, okay, yep.
Hope for you later.
Okay, sounds good.
Okay, so if there's more questions, maybe you can talk to David after. Time for lunch. So let's thank David again.
The question was about I get why the base of the like taking a bundle view. Yeah. I get why like counting how many things are at the base.
Yeah.
Yeah. But the
to make sure that we are in the. Yeah.
There's actually an extra one.
He came in like a minute ago and then left again.
Nice to meet you. I'm Lorand. I'll be actually chairing this session. You have 4 minutes with questions, and I'll be giving you a 5-minute warning. Somebody's gonna help me to put the mic. Unfortunately, for the few versions on the screen, this one's the final version. Yes, I think that's the one that's the final. Yeah. Can I just double check it? Yeah, absolutely. Okay, it's not the final, it's okay. Oh, it's easy. I'm sorry about this because I'm. It says I should have used a better version in the system. It says final, the correct one, or like final version.
You have a date there. That one's final. These two.
That was the one I found.
Okay, then that's it. A quick etiquette question. Can I remove the mask during the talk, or it's best if I keep it?
What is our stance?
It's perfectly okay to remove it because you're far away from it.
I think generally we're not requiring people to wear them. We just have courage.
And this is like this. It works.
And you should put this in your pocket.
And this one, just quick check. Perfect. And it points with the red.
Yes, I think so.
Perfect.
Did you share? Oh. Hello, everyone. Welcome to the afternoon lens and optics session. So we're going to have 3 talks, and the first one is a distinguished presentation from Clere on dependent optics.
Okay, so can you hear me? So hello, everyone. First of all, I'd like to thank the organizers for the opportunity to present my work here. And today I'm going to talk about dependent optics, a broad generalization of lenses, which themselves are a framework for bidirectional data transformations in functional programming. Now, full disclosure, I'm new to optics, lenses, as well as functional programming. So my interest to this field stems from its applications in machine learning. So I will try to
I was saying, so I will try to explore the machine learning point of view throughout the presentation.
Sorry.
I'll be unfazed. So let's start with the basics. So lenses, which is something that we've known about for a pretty long time now. So in this talk, I will first of all introduce lenses and their initial applications. Then I will describe a generalization, so functor lenses in general and dependent lenses in particular. And I will move on and discuss why I think lenses are useful for reverse mode automatic differentiation, which is the primary machine learning application that I have in mind. I will then switch gear and introduce the framework of optics and their novel generalization, dependent optics, which is the kind of crucial part of this talk. I will show how dependent optics compare with functor lenses and how they can be used to unify different theories. And finally, I will tackle the problem of dependent optics representations. That is to say, how to characterize functors from the category of dependent optics to an arbitrary category. But first of all, let's start with lenses. So lenses are a useful abstraction to access and update data structures. So this one here is a simple code snippet in Julia, but it really looks like a pseudocode, where we have a simple structure that represents a person. So it has a name field, which is a string, and an age field, which is an integer. And we're interested in interacting with the age field. And to do that, we need two methods. We need a get method, in particular getAge, that given a person will return their age. And the put method with a slightly more complex signature that will be used to update the age. So it will return a new instance of type person with the same name as the original and an updated age value. So more formally, this is done by means of two methods which work in different directions. So we have the get method that goes from the whole, so the person, to the part, the age of the person. And the put method, which is in some sense reversed, because from the part we get the whole, so it goes in the other direction. So bidirectionality is a key feature of lenses, and composability is the other one. The key intuition is that sometimes our data structures are nested. For example, these person structures could be embedded in a complex data structure, maybe a team with a supervisor or some students or a list of persons. And in this case, to access and update data, we want to use the composed lenses. Now, the composition is very easy for the get method. So we simply compose get one and get two, whereas the put method is less straightforward. So you can compose, it forms a category, but you have to do this little dance over there, which to be honest, I find less than ideal. It was one of the things that bugged me a little bit. And I think this composition becomes much clearer in a more modern generalization of lenses, functor lenses. So these are a more modern framework and much richer that was recently put forward. And the setting is that one would work with a category C and with a functor F, contravariant functor, from C to cat, the category of categories. Now, cat is actually a two category, because it has categories, functors, and natural transformations. So it's more precise to say that this is actually a pseudo functor, but we don't need to worry so much about this technical detail. And the idea is the following. Once we have such pseudo functor, we can build a category where the objects are these pairs. I'm going to read them P over X, where X is an object in C. So C is some sort of base category. X is an object in C. And then P is an object that lives on top of X. So more formally is an object in the category F of X. So the category associated to X. Now, once I have two of these things, so P over X and Q over Y, I can consider the set of morphisms between them. And the framework of functor lenses said that to define a morphism here, I need to do two things. So first of all, I need to decide the mapping F between the base spaces. So F goes from X to Y. And now once I'm equipped with F, I can use F star to pull back Q so that now it lives on top of X. So in the same category as P, and I can consider morphisms between them. Here I'm slightly abusing notation, so I'm using F star as a shorthand for calligraphic F of F. The key idea being that F is contravariant, calligraphic F is contravariant, so I can use it to pull things back. And this construction feels already familiar coming from lenses because it shares the two most important properties. It is bidirectional in some sense, because we have F that goes forward and F sharp, which is how I'm calling the morphism from F star Q to P, that goes backward, goes in the opposite direction. And again, it is composable. So this follows by the functoriality of F star and also the functoriality of calligraphic F. So one can indeed prove that these functor lenses form a category. Now, as a sanity check, it's of course important to show that we recover classical and plain old lenses as a particular case of functor lenses. And the idea to do that is slightly convoluted. So one would start with a category that has products. And then one has to notice that if you fix an object X, taking the product with X is not only an endofunctor, it's actually a comonad in this category, the product comonad. And so you can consider its Koch-Leslie category. And this mapping from the object X to this Koch-Leslie category is contravariant. And so you can use it to build a category of lenses. And it's straightforward to verify that we get the same thing that we had at the beginning. So we get something where morphisms are an arrow from X to Y and another one from X times Y prime to X prime. Now, of course, this isn't the only example of functor lenses that one can come up with. There are many more, but the only other one that I'm going to show are dependent lenses, which are kind of a very nice generalization of plane lenses. And the idea is that we can consider the slice functor that to each object X associate the category of objects over X. So it's basically objects U equipped with a map to X, and they form a category. And if in C we have pullbacks, then we can use pullbacks to kind of move things around, and this becomes a contravariant functor. And we can simply spell out the general definition in this case, and we get the definition of dependent lenses. I mentioned that this is a generalization of lenses because lenses are embedded in there. The key idea is that if you have just a couple of objects, so XX prime, as we have with the object in lenses, you can associate to it the product projection, basically from X times X prime to X. And in practice, you recover lenses within dependent lenses as this kind of trivial bundles, the bundles that trivialize as a product. Now, of course, there's more stuff because not all bundles are trivial. You have bundles that don't trivialize. And this intuition should be quite clear if one is coming from, for example, differential geometry. If that's kind of not at all your background, but you come rather from, for example, a type theory background, for the purpose of following this talk, I think it might be helpful to think of the map U to X as some sort of dependent type parameterized by X. So these will be our two kind of primary examples. And I would like to make the case that both these examples are very relevant for reverse mode automatic differentiation, which is a field that is booming recently with the boom of machine learning. Now, the basic idea of reverse mode automatic differentiation, expressed in extremely formal terms, is that you can pull back cotangent vectors along a smooth function using the dual of the differential. Now, this is a bit of a mouthful and may sound maybe slightly obscure, a more kind of down-to-earth notion is that if you have a smooth function between manifolds, then you would have the tangent spaces that approximate the manifold linearly, and the differential, which is the linear local approximation of our smooth function around a given point. And so it's a linear map between the tangent spaces. And if we take the dual, we'd have a linear map between the cotangent spaces that goes in the opposite direction. And the kind of the core tenet of reverse mode automatic differentiation is that you should be basically the computer should be able to figure this out, what this mapping is, based on the way that you have implemented your smooth function f. So you implement your function and then the software on its own figures out this mapping. Now, for the sake of time, I will completely butcher this field of research and give a caricature of the procedure that you would use for this thing, which is a reasonable way that you would use if you're working with it. You would think, okay, for some primitive functions, I will just hard code it. It's going to be some lookup table where for each function I write it down what this is going to be, and then if I have a more complex function, it's going to be the composition of simpler things. So I just need to apply the chain rule to get the mapping from the output all the way back to the input. And as simple as this sounds, in principle, this is one of the key technical difficulties in modern machine learning, because to optimize the parameters, you need to compute the gradients. But writing a machine learning model is quite complex per se. So you don't want to require the user to also write the gradient. That would be very hard, very error prone. You want it to be computed automatically. And you want this to be fast because the bulk of the training happens in this reverse pass. So this is not kind of a purely academic discussion. A performance improvement in reverse mode differentiation would have massive relevance in terms of sustainability of machine learning techniques. And I think that it's quite close to what we are doing because the link to lenses in my mind is quite natural, because reverse mode differentiation is naturally bidirectional, because to compute the gradient, you go in the reversed way compared to the forward way, which is what you use to compute the value. So the value is actually called the forward pass in machine learning, and the gradient the backward pass, because it's quite clear that you go in different directions. And similarly, composability is a key feature because you are mostly, the whole framework rests on the idea that for function composition, you're going to just use the chain rule to compose differentials. So what I want to do here is to show in a simple example how one can build a lens that corresponds to this reverse mode differentiation. For simplicity, I'm going to start with a smooth function f between two Euclidean spaces, x and y. Now, I'm not asking that f is linear, but just that it's smooth. And the idea is that now we can define a lens as follows. As I briefly mentioned before, the forward pass will just be our function f. So f goes from x to y, it goes in the forward direction, all is well. And the backward pass is slightly trickier, but if you have a point in the input and the dual vector in the dual of y, we can first compute the differential that goes again from x to y, its dual from y star to x star, and apply to the vector v. So in other words, the forward method is given by the function, and the backward method by the dual of the differential. Now again, this is bidirectional, so value and derivatives are computed in opposite directions. It's composable, because if you write down the form, that somewhat complicated formula for lens composition, you actually get the chain rule. Unfortunately, it is inefficient. Like, this is kind of not an efficient way to write that. And the reason is slightly subtle. The idea is that, and this is quite clear in practice, if you write down a deep learning model, for example, a sequence of layers, is that in a forward pass, you will be calculating a bunch of variables that are actually quite useful for the backward pass. So you don't want to recompute them all the way over. But in this framework, there's no way to tell the backward pass where they would look for them. So an approximation that I write in this form of an implementation of the dual of the differential written in this form kind of has no way to be smart about this. And I think this motivated kind of a large chunk of the rest of the talk. So how can we find a smarter way about this, to use lenses as an efficient technique for automatic differentiation? And a possible technique is actually more of a programming trick than a math trick, even though it's somewhere in between. And the idea is to use closures. So basically, if our category not only has products, but it's a Cartesian closed category, so I have an internal home object, I can actually consider a summarized version of the forward and backward pass as a unique mapping that takes as input an element of x, and then it returns not only an element of y, but also a map from y prime to x prime. And the reason why this is more efficient is that here, as I'm returning these two things together, as I compute f, I can be kind of mindful of what variables I'm computing, kind of keep them inside. And when I write this, when I implement this bit, I will actually just read those variables. This is called the closure in programming, because in the programming jargon, you close over those variables. They become part of the function. And this works quite well in practice. And indeed, to the best of my knowledge, it is how kind of the most well-known automatic differentiation libraries from deep learning frameworks would do it. If you were to use, for example, PyTorch or TensorFlow eager mode, kind of under the hood, they would be doing something pretty much like this. However, there are also two kind of clear disadvantages. On the one hand, it's what I was saying before, that this is a bit more of a programming trick in that we don't have a clear representation of shared computation. So it is recorded somehow because it's hidden inside the closure, but it's not part of our framework. Nowhere here have I written what are these variables that are shared. And the other problem is that actually lenses aren't quite enough for this, but you should use dependent lenses for two reasons. One is kind of a conceptual reason, that for a vector space, the cotangent bundle is a product projection. It's trivial, but in general, it's not. And you need dependent lenses for non-trivial bundles. So philosophically, you need them. But even in practice, they're much better because they give you coproducts, unlike lenses which don't have them in general. And this is crucial because you need those in programming for some types, for control flow. Like you don't go very far without coproducts in programming. But unfortunately, if you are to use dependent lenses, this trick exists, but it becomes a bit trickier to write. I think it's a bit more unwieldy. So I would actually like to suggest a completely different approach that tries to solve these two issues. And this is my interpretation of why optics are interesting. So the idea is that we would be explicit about a space M of shared data between the forward and the backward pass. Now here, for consistency with optics, I'm going to call forward and backward L and R, the left and right morphism, where L basically takes the input and gives me not only the output, but also some extra stuff that it has computed along the way, and it doesn't want to throw it away. And in functional programming, if you don't want to throw it away, you have to return it. It's the only way around it. And R, it has not only our dual vector from y prime, but it also gets this extra information. It remembers it, and you can use it to write an optimized R that would return the output using this extra data. The main conceptual problem is basically how one would select M, because we can't really fix one. There's no one-size-fits-all approach. Taking the coproduct over all possible M's, that would also not work. It would become actually not a category for technical reasons. And this complicated beast is the correct answer. So this is called a coend. I'm using the integral notation. And the idea is that it's almost like a coproduct in that the first step is to take the coproduct of these objects, but then it adds on top of it an equivalence relationship, which is induced by the morphisms in the category C. I'm not going to go into detail, but I encourage you to read up on ends and coends because they're quite interesting formalism. And the key remark is that if we do the coend, we get something that is exactly equivalent to lenses. So it's the same as giving a get method from x to y and a put method from x times y prime to x prime. But of course, we are presenting it in a very different way. The way we are presenting it, Cartesian optic is an equivalence class of a pair of maps where the equivalence class is given by the coend. And the key difference is that this is naturally efficient because the morphism R, it will read data from M instead of recomputing it. And again, this has already found some application. So I'd like to cite the diffractor.jl Julia library, which is a kind of cutting edge library for automatic differentiation that is already based on the formalism of optics and dependent optics. And of course, once we transition to this scenario, we can generalize it in so many possible ways. I think a prominent generalization, which is due to, well, at least I know it from Riley a few years ago, is based on the idea that you don't need the Cartesian product at all. Any symmetric monoidal category would work. You just replace the Cartesian product with the tensor product and all is well. Of course, with the only important difference that you can't write it explicitly. So you don't have a closed formula, but you don't need to have one. You can kind of stick with the coend. And more recently, there was a paper in 2020 that explained that actually you don't even need the tensor product. You could have a category M acting with these two actions, .L and .R, on two different categories, CL and CR. So these things are called actegories. It's a play on word for action of monoidal category or another category. And if you have this, again, it all works. You can define a category of optics called mixed optics. What's the unsatisfying thing about this is that we wanted to get functor lenses as an example. We wanted to specialize to those, but this doesn't work because in functor lenses, we had a pseudo functor to cat. We don't have the actegory and we don't know how to get the pseudo functor from the actegory. Well, we do. Not all pseudo functors arise from an actegory, so it's a bit tricky to fix. And this actually can be solved with a very cute higher category trick. The idea is that this is actually well known, it's called delooping, is that a monoidal category, you can think of it as the morphisms of a bicategory with one unique object, because you have a notion of composition of these morphisms. And this operation is called delooping, to go from monoidal category to bicategory with one object. And once you do this trick, the actegory is turned into a pseudo functor. So now you have enough to also get the functor lenses. And this is such a natural and kind of almost pleasant way to proceed that a bunch of people, semi-unbeknownst to each other, so Bartosz Milewski, myself, and Matteo Capucci, we kind of proposed this idea almost simultaneously in a series of papers. And with the key trick that, of course, there's no point to require the source by category to have just one object. You can have as many as needed. And indeed, this will be our primary definition, the notion of dependent optics. The setting is that we have a bicategory and I choose them to be contravariant pseudo-functor from the bicategory B to cat, the two category of categories. And once we have those, I can build the category as follows. The objects have the form x prime A, where A is an object in B in our base category, and then X lives in the left category over A and X prime lives in the right category over A. In principle, they can be different. And if I have two such things, so X prime A and Y prime B, I can explicitly say what the morphisms between them are, because they're again a coend, but this time the category that I use, it varies. It's the category of morphism between A and B. And I use these morphisms with the same trick as we were using for functor lenses. So to pull back Y to the category over A when originally it was over B, and I pull back Y prime to the category again over A when originally it was over B. Where again here, I'm saying F star and F star prime, where really it is the functors L of F and R of F. Again, contravariant functors, we can pull things back. And it turns out that this is our general definition that we're going to use to encompass all the examples that I've shown so far. Even without seeing in detail that they're all included in this, we can see that it has the same flavor, because again, it is bidirectional, because the bit in L is the forward direction and the bit in R is the backward direction. And it is composable. So this is slightly involved to prove formally, like I struggle through pages and pages of coherence morphism, but you can do it. So it follows from the functoriality of F star prime and also L of L and R, that you can compose dependent optics. And indeed is our kind of first big theorem that dependent optics form a category. And I'm gonna leave the formula here because I think it's very helpful to have it in front of your eyes to understand how it specializes to different things. And the first trick is to see how we get back mixed optics. And that's actually very straightforward, because again, if this is the looping of a monoidal category, then there's only one object, so A and B, I don't have to bother writing them. This is a unique category M that has to be monoidal, and I get the exact same formula of mixed optics. So this is actually the most straightforward of the two. And the second example, functor lenses, we also get that because we can choose a plain one category as B. So all the two morphism, the kind of B-categorical structure is all trivial. And also L, we decide that it is trivial. And then basically, if calligraphic B is a one category, this is a set, then the coend specialized to a coproduct. These I forget about because I picked it to be trivial, and it's exactly the same formula as we had for functor lenses. So we specialize to both. And to be honest, another disclaimer, it is much clearer to me to think of dependent optics as generalized functor lenses. And in what follows, I'm gonna try and discuss what properties of functor lenses we wanna bring over to the kind of more general realm of dependent optics. I will start with the success story to give some optimism to the room, and is the question of coproducts, which we have mentioned already are very important, and you have them for dependent lenses, and there's a general result that establishes when you can expect to have them with dependent optics. So basically, if you are in a bicategory B with finite coproducts, which is also well defined for bicategories, there's a notion of coproduct there, and the functors L and R are contravariant, so they're going to turn them into products rather than coproducts, because the arrows are flipped. If that is the case, then also the category of optics will have finite coproducts and are the kind of the natural thing that you would want to write. Your kind of first guess is the correct one. And then kind of to reset expectations a bit, I'm going to go for the kind of a failure story. That with functor lenses, it's very nice because you do have a base category, and it really is a base category. You have a nice vibration, which is a very well-behaved functor from lenses to their base category. Here you don't, because if I choose a morphism over here, it's going to be an equivalence class of these things. So it's not very well defined what F I'm going to associate to it. But in my mind, it's a silly reason. It's not a real reason. So I think there's a remedy to this, which is basically not quotient this. You just keep the coproduct, and instead you accept that you're going to work with a bicategory of optics, where the coproduct of these are one morphisms, and the equivalence relationship, you actually just put two morphisms between them. And then it is my intuition that this vibration should exist, this functor at least should exist. So this we can recover it. And last one is not done. I was trying to nerd snipe other researcher into working on it over a lunch break with mixed success. Let's see in the following months how that went. But oh no, it's covered. But so for functor lenses, we have a monoidality result. So if the base category is monoidal and the functor is lax monoidal, then the functor lenses are lax monoidal. I think the same holds here. So if B is monoidal and the two functors are lax monoidal, then you get the same result. Oh, that's super late. But I also think that that it's very hard to prove, but it could be easier to prove if you were to work with monoidal double categories that are a bit of a friendlier notion. Now I'm going to actually go through some more delicate part, which is something that confused many people. So basically, that functor lenses, we get them in a very weird way. So why is L trivial? All trivial, two morphism. This feels like we lost a lot of the framework. We can no longer use F to share computation because it became the forward part. And the good news is that for dependent optics, but I think it's quite general, we can circumvent this. And the key trick is to remember what we had done for regular Cartesian optics, how we got lenses. We just wrote this coand and computed it explicitly. And a trick that always worked, well, in my kind of playing around with pen and paper, always worked with the dependent optics, is to replace products and tensor products with fiber products and tensor product over some base. So here, if we just use a fiber product instead, and so now we have to use a category of spans where M is not just an object in C, but in C over A times B. Then we can explicitly compute this, and we see that we are going to recover dependent lenses in a different way, which seems more natural because again we have our M to store our computations. So we actually, this is the one we wanted. But this raises two, let's say, philosophical, frequently asked questions. Because there are things that have bugged me and have bugged many people. I've been asked a few times about this, so I thought it's a good moment to tackle those. And one is basically, which is it? How can it be that I have two radically different but natural choices of pseudo-functors to get me the category of dependent lenses? Should I pick one? And my answer to this is that there is one unique category of dependent lenses, but two B categories, if you remember about the information in the span. And those are distinct. So it's natural that you would have two choices of pseudo-functors to recover these two bicategories. And even in the classical example of optics, Cartesian optics and lenses, I would argue that those are not the same. They are different as bicategories. The implementation is different. And so it's natural that if I generalize both, I'm going to generalize them in distinct ways. And the final frequently asked question is, what does it mean that L is trivial? What is the forward part if L is trivial? And my answer to this, and this again becomes clear if you think in terms of coproducts and we keep the whole bicategory without the quotient, is that actually F from A to B, that's also the forward part. So really, this object here, the one where you forget about R, but you keep the coproduct, is the forward part. And the value of your morphism inside the fiber on top here, that's the backward part. So you do have a non-trivial forward part also for functor lenses. You actually recover the same one. So I think this is the correct intuition, this kind of map. And so that's all I wanted to say about the category of dependent optics. I hope I still have time, because this is actually quite interesting, to discuss a more practical aspect, which is more on the programming side. So if I write...
yeah, you're running into your question time, but you can...
it's my tradition, just power through the last slides. I will do this. So the basically the key question is, if as a library, and if Fractor.jl did it already, I'm using these optics as an implementation internally, then this F thing, it's still defined, it's in an equivalence class. How do I hide it from the user? I cannot allow the user to rely on this. And I think there are two answers to this. One is that you compute the coend explicitly, but of course that's not possible. And what if you find something that you didn't want with the coend? What if that doesn't look efficient? And the alternative actually comes from the theory of group representations. Okay, the group is complex, but functors from it to vector spaces are easy. And so here you can consider, you can basically consider functors from the category of optics to a friendlier category that you know how to deal with. And the good news is that these are easy to characterize. So if you pick an arbitrary category, then you can define a Tambara representation, which is a generalization of a Tambara module, which was a previous theory, well, a previous notion even before optics. That is a reasonably straightforward definition as a family of functors with a covariant and contravariant component, and of natural transformation respecting some laws. And the last important theorem of my manuscript is that a functor from the category of optic, contravariant functor from the category of optic to D, is the same as a D-valued Tambara representations. And well, I will not go into detail, but it's actually very easy to come up with examples of these things. For example, pulling back differential one forms along smooth maps is one of the interesting examples that is most remindful of our reverse mode differentiation example. And this is everything I wanted to say. So dependent optics are a simultaneous generalization of mixed optic and functor lenses. They can be used to efficiently represent bidirectional transformations. They're a nice category in that they have finite coproducts under simple assumptions. We don't quite generalize the functor lenses fibration, but we are hopeful we can do that with bicategories. We need to work out a monoidality theorem, which could be technically involved, but I believe in it. And the category of representations is kind of well-behaved and simple to describe by means of Tambara representations, even though it remains to see what this would look like for kind of special cases of dependent optics. I haven't worked it out yet, but it's an interesting future direction. And that was all. Thank you very much, and sorry for running over.
Thank you, Pietro. I think we have time for one, maybe two quick questions.
So you've been talking about diffraction, right? And as you kind of feature knowledge, so is there like an implementation? Like, is there code implemented?
Yes, well, yes, there is. So the code, there's a bit of a divide in that it's implemented. Yes, there is an implementation of optics in Julia, not dependent optics, but then in the documentation justifying what he's doing, Ken has to hand wave because he really needs coproducts but can't get them, and mention that this should be somehow some predicated coproduct. And I think that really you need dependent optics. I think that morally that's what the library is using, but I'm not sure implementation-wise what differences you would see.
it's not so much a question as much as a historical note, like this paper and he didn't generalize it to Categorification optics, as he says in his paper. It was as for the street. Just like what people want to agree on.
Thank you. Yeah, I suspect that I was missing on earlier literature. Thank you for pointing that out.
So I think we can thank the speaker again. Next up, we have Bryce Clark, who's going to be telling us about enriched length.
All right, thank you, Bruno, and thank you to all the organisers. Really great job so far with organising, and it's been a great conference so far, and I hope it keeps going throughout the week. So we just heard a talk about optics and a certain kind of lenses. I sort of want to switch track and talk about a different kind of lens. So if you sort of know me or know any of the work that I've been working on for the last 4 years or so, what happened? I'll keep talking. I've been working on a kind of lens called delta lenses, and they're kind of lenses between categories. And sort of some of the motivation behind why I'm talking about enriched lenses today is that last year, Paolo Perone came up with a different kind of lens called a weighted lens, and they're lenses between weighted categories. And I saw this paper and I thought, oh, this is great. It's like a delta lens, except with some more stuff going on. And I sort of wanted to go through and prove a bunch of theorems and so about weighted lenses. But then I sort of paused for a second and I thought, there's probably a smarter way to do this and find what's the common generalization for these delta lenses that I've been working on for a long time and these weighted lenses that were just introduced. And so me and Matthew D'Amelio, who is unfortunately sick at the moment, came up with this common generalization of enriched lens. So that's what I want to talk about. So to give a bit more sort of overview of motivation, I sort of want to start with this sort of phrase that lenses model these things called bidirectional transformations. And so sort of the framework that I want you to have in your head is to think of sort of these spaces A and B, and think of them some kind of system, as you like, and we want to think of these systems as categories. So the idea is that the objects of the categories are some kind of state, the states of the system, and the morphisms of the categories are like the transitions or the updates to the state of the system. Okay, so that's what we're thinking of A and B as. And lenses are sort of, as I'm describing them, come with sort of three parts. First, we want some kind of object assignment between the states of these two systems. Okay, and this is sort of modeling consistency between the states of these systems, right? So if we have a state, which I'm giving a dot down in our system B, the fiber above that state with respect to this object assignment are all the states that are consistent with it. Okay, and so lenses typically have two parts. They have like a forwards part and a backwards part. And so for this framework of lens, our forwards part is modeled by a functor. Okay, and so here up in A, we have some kind of transition or updates between states. And using our functor, we can propagate that to some kind of transition or update in our system B. Okay, so this is some kind of, if we start with a state and we move into some different state, the functor sort of restores consistency with our state in B in a forwards direction. Okay, so that's the forwards part of the lens, but we also know that lenses have some kind of backwards component. And so this is what the cofunctor of these kinds of lenses that I'm working with does. It's giving you some backwards consistency restoration. So the idea here is that we start with the state a state in our system A. We use our consistency relation to get a state, corresponding state in B, and we make some update or transition. The cofunctor is then lifting this transition to some transition in A, which is consistent with it. Okay, and so these three things together give this classical notion that I've been working with called a delta lens. There's some sort of other axioms and stuff that relate these things together. And so I guess the point of generalization today, this sort of mathematically motivating question, is that we can ask the question, well, what's the correct way to restore consistency between systems if they're somehow enriched in some way? And so in the case of weighted lenses, which is sort of the main example, this enrichment is sort of saying, well, we can put some kind of cost or weight on our transitions or updates in our system and ask, well, what's the correct way to propagate transitions now when we've got to respect this weight or this cost somehow? Another example is you can think of our Helm sets in our systems, and you might say, well, what if we can add our transitions or our updates together? We've got some kind of enrichment in commutative monoids or abelian groups. How do we appropriately do cofunctors and lenses in that setting? And so in this talk, I sort of want to do two main things. I want to introduce the notion of enriched cofunctor and lens, and then I want to sort of share some examples of these things, including weighted lenses. Okay, so enriched lenses versus cofunctors, enriched cofunctors. So I sort of just want to introduce these two notions and sort of see them side by side and see how they're similar or different with each other. The sort of underlying assumption for this talk, so I'm talking about things between enriched categories, and I'm assuming that the base of enrichment is a distributive monoidal category. This is a really important assumption, but we don't actually need it for enriched functors, but we do need it for enriched cofunctors. So an enriched functor, if you sort of already know this, then I sort of don't need to tell you all the details, and if you don't, then maybe this won't be enough either. But it's sort of, it consists of two parts. It's got some object assignment between the objects of our enriched categories, and it's got a family of maps between our Helm objects, which are objects in our base of enrichment V, and these satisfy some axioms. Okay, and so if we look at the case where our base of enrichment is weighted sets, so sets where each element has some associated real number, positive real number attached to it, then when we enrich in this thing, we get weighted categories and weighted functors. So they're just functors where if we have morphisms with some associated cost, the weight of the image has to be less than or equal to the weight of the original morphism. Okay, so that's enriched functors. And then we also have this notion of enriched cofunctor, which sort of at first glance looks a bit more complicated. The first part of the information is the same. We still have some object assignment between the sets of objects of our enriched categories, but now we have this family of maps, which I'm using phi AB. So that's a family where A is in A and B is in B. And so it's a family of maps from these Helms. So we have from this Helm, but now we're going into a sum of Helm objects. And the sum is over the fiber with respect to this object assignment. Okay, so there's some kind of extra technical conditions here, which are actually really important because I haven't included the axioms, but we need them for the axioms which to actually work. Okay, so we're looking at these two definitions side by side of enriched functor and enriched cofunctor, and they look kind of different, but it turns out that they're actually completely dual to each other. The trick is to think of these things here, and we can sum up over all the possible A primes. Okay, if we do that, we actually get something out of a sum of Helms where we're looking at, again, the same fiber with respect to our object assignment. And this is just an equivalent definition of an enriched functor, right? They're the same thing because we're mapping out of coproducts. But now when we look at these two definitions, we see that they're exactly the same, except for the fact that, well, we have the same object assignment, but our family of maps now are just in the opposite direction. Okay, so this is really sort of clarifying some of the duality between functors and cofunctors and looking at it in an enriched setting. Okay, and so we also have this example of weighted cofunctors where we enrich in weighted sets, and we now ask that the weight of the lift is less than or equal to the weight of the original morphism in our codomain. Okay, so I mean, they're enriched cofunctors. They still look maybe a little bit scary or unfamiliar or more complex than enriched functors. And so you might ask, well, what's some ways in which we can make these things a little bit simpler? And we can do this by adding some extra assumptions on our base of enrichment V. Okay, so here we add the assumption that's an extensive category, which just means that it has, well, it already had coproducts from distributive monoidal, but it also has some pullbacks which behave well with these coproducts. Okay, and if we add this, just this very mild extra assumption, we get this nice little result which says that enriched cofunctors are the same as spans of enriched functors. Okay, where the first enriched functor has the object assignment invertible, and the second enriched functor has this map invertible. So if you look at this map here, it's the same as this map here. So the span is of two spans of functors where each one of these two parts of an enriched functor, one of each are invertible. Okay, we can also see this as some kind of factorization system on cofunctors where we have a cofunctor from A to C and from C to B. And so it sort of breaks things down and makes things a bit easier to understand. And so we can again look at this example of weighted cofunctors, and we can see here now that a weighted cofunctor from A to B can be sort of broken up into these spans of weighted functors. So I won't go into this example in detail, but that's just to sort of demonstrate that it has some kind of value looking at this sort of theorem here. Okay, so what's an enriched lens? We now put these things together. So I've got this big box here with an enriched lens at the top. And I sort of want to see this as some kind of Venn diagram. The things inside are enriched lenses. So the first part of an enriched lens is an enriched functor. Okay, we just saw what those are. The second part is an enriched cofunctor. But now we ask at the enriched functor, the object assignment is the same for the enriched functor and enriched cofunctor. And now we ask for some compatibility axiom. So we ask that if we apply the family of maps for our enriched cofunctor, then we apply the family of maps for our enriched functor, we get the identity. Okay, so it's just like going upwards and then going back down, we get back to where we started. Okay, and then we have these weighted lenses as well. And so we actually have this stronger condition now that the weight of the lifts has to be equal to the weight of the morphism. Okay, and so on this slide, we see like a bunch of examples of enriched lenses. So set is just the basic case. They get you back delta lenses again. We're mapping now, we're lifting morphisms from f of A to B to something in this HOM, this sum of HOMs. We enrich in weighted sets, which is sort of the working example that we've seen. The coproduct is disjoint union, and we have this extra condition. We can enrich in this interval category as a poset with infimums as the coproducts. And so enriched categories here are Levin metric spaces. The enriched functors are weight decreasing maps, I guess. And the enriched cofunctors are adding extra conditions on like this. And so submetries are an example of this. I have a few other examples here of abelian groups where our coproduct is actually a byproduct. We get some nice things going on there. And also for any monoidal category we like, we can take its free coproduct completion and enrich in this. And then we also get examples of enriched cofunctors and lenses here. So just to finish off, I want to sort of tie this all together and say, well, why is this notion correct? I mean, maybe I've convinced you already, but if you're not convinced, you might think this is a bit ad hoc or something like this. So what's the general framework? The general framework is that if you start with any double category with companions, we can build some new double categories. So we can build a double category of monads, monad morphisms, and these things called monad retromorphisms, which I don't expect you to know about. And then we do this other thing called this right connected completion to this double category. And the idea is that this final double category here, the one class of the morphisms of this double category can be seen as lenses between monads. And so the idea here is that if this original starting double category D is mat of V, we get out enriched categories, functors and cofunctors. And if we start with span of E, for E with pullbacks, we get internal categories functors and co-functors, which is something I spoke about at ACT a few years back. And we also have this example of the filter monad F. We can look at its Kleisli-like double category, and we get topological spaces, continuous maps, and open maps out. So I thought that was really nice to see this sort of general double categorical framework for lenses and so on. And so just to summarize, this is sort of a bit of a diagram or a picture about everything I've spoken to you about in the talk. I won't go through that again. Some future work is, I guess, we want to look at more examples. So for example, V is equal to poly. David's already talked about all these nice monoidal structures and distributed monoidal structures. And I think he's already wrote a paper about looking at monoids with respect to these things. And if we look at enriched categories as generalized monoids, we can sort of get a more general notion of collective. Also, if we look at a monoid and we look at its power set, we also get a monoidal category. We can look at enriching in that. And there's also these theoretical questions about, can we better understand enriched split op vibrations using enriched lenses? There's some kind of least change notion of lens. Can we look at some Groton deconstruction for weighted lenses? I think would be really interesting, or perhaps even look at some enriched setting for this. And also looking at two cells between enriched co-functors is something I sort of know, but I didn't have time to talk about today. And so that's it. Thank you very much.
Very much, guys. Are there any questions? Hey, Brian, it's really nice talk.
Thank you.
Can I ask, have you thought about delta optics?
Right. Okay. So yes. So this is a really good question. I mean, I don't have a good answer, but I guess that's one of my challenges to all these very intelligent people in the room, is that if you can somehow bring together delta lenses or even enriched lenses with optics or dependent optics or things like this, that would be wonderful, because I guess these things sort of branched away from each other, a decade or so ago, and it'd be really nice to bring them back together as some kind of nice piece of category theory and applied category theory. But yeah, no idea yet.
So for example, the min plus semi-ring, you said that an enriched lens was an endometry or something. I wanted to ask what that was.
So let's go back to the example slide. So for this one here, yeah. So what did you want to know exactly?
What is that?
Right. Okay. So that's probably not so easy to explain in the period of time that I have. But if you look at the extended abstract, and especially look at Paolo's paper, he sort of goes into this in more detail. But yeah, sorry. Thank you for your question.
Right in that example, why is there an inequality there? Because all other cases seem to have something like equalities. Is there like a short reason why, or?
I see. So I guess, yes, that's a good point to raise here. And the reason is that I haven't been inconsistent. Some of these lifting maps are for enriched co-functors and the others are for enriched lenses. And so, yes, this is the quality for lenses. Yes. Yeah. But yeah, for the co-functors, we just have inequality.
Are there any other questions? So I guess there was also a notion of internal lenses for the categories, and there are also fixed lenses.
Yes.
At this point, I would like to ask if there's a notion that I can do like some sort of formal category there, so that I can have it. When this makes sense, like something that generalizes formulated for construction.
Yeah, so that's really what I'm doing here. Is this double category approach, and especially looking at this right connected completion business, is some kind of common generalization of the internal and enriched approaches to lenses. And so, yeah, I gave a talk at Intercats online this year where I sort of really pushed hard this notion of lenses in a double category. And this is sort of, I guess, the common generalization that one could look at further.
Thank you.
think actually we still have time for maybe one more question. Getting bombarded.
Yeah, well, that's great.
Thanks. This is not a very well-defined question, but just it relates to something that John Baas has talked yesterday about. So you have the definition of co-functor. So you have the co-product on the outside.
Mhm.
So if the category has co-products, and you move that onto the inside.
I'm not sure what you mean by inside and outside.
Sorry. You've got the definition of co-functor there.
Yeah. Let's go back. Yeah, here.
Yeah. So on the right-hand side there, so you've got sum over the hom object.
Yes, that's right. Yes.
So if you move the sum inside the hom object.
Ah, right.
Then you get something that looks a lot like an adjunction between F and F inverse.
Right. Okay.
So, and this sort of seems to be related to the stuff John was talking about with structured and decorated co-spans. Being similar when you have a vibration with a
Okay. Yeah, no, that's an interesting comment. I will have to think about that a little bit more. Yeah. Thank you.
And I think we should thank the speaker again.
That's right.
So I need the mic myself.
Yes.
What the hell? Hell of a clip. Is it on now?
Yes, it is.
Okay. Let's hope it works. Does it pick up? Okay.
And I'd like to welcome our last speaker of this session, Chad Nestor, who's going to be telling us about coordinate optics.
Yes, thanks. So I'm Chad Nestor. I'm a PhD student at Tallinn University of Technology, which is in Estonia, with Paavo Sobocinski. And I'm going to tell you today about something that I've been working on for the last little bit together with Guillaume Bousseau and Mario Roman. And the thing that this is about is optics in the sort of old-fashioned sense. I mean, we saw just this session a lot of kinky versions of optics where we might take this sort of thing and generalize it in this direction or that direction. And before we start, I'd like to suggest that maybe part of that is that when you look at the sort of elementary definition of optics or lenses from this original stuff on bidirectional transformations, it's pretty weird. And the thing I'm going to show you today is a way to understand this definition in nice categorical terms. And then we'll start doing that now. So we'll recall first what are optics in this sort of elementary sense. And always we're going to be in some monoidal category, sort of blackboard bold A. And so optics in A are pairs subject to some equations. We'll do the equations on the next slide, but for now, an optic is a pair alpha beta, say, and the objects of this category of optics will be pairs of objects in A. And an optic from AB to CD will be a pair alpha and beta, where A, as you see sort of pictured in this informal diagram on the slide here, takes in something of type A and gives me back something of type M and something of type C. And I send that thing of type C out the other side of it. I send the thing of type M into the B component of my pair, get something of type D from the other side, feed that into the beta component, and then get something of type B out the original side. And so this is the sort of bidirectional transformation. You know, it goes this way and then it goes that way. And I get to share some information between these two things. And if you've encountered optics and they're not like a thing that you study, you've probably encountered them as lenses, which traditionally are optics in a Cartesian monoidal category. So I told you that optics were not just pairs, they're subject to equations, and in particular, they are subject to these sliding equations, which tell me that if I'm going to sort of do something to that shared information wire in the first component, then I could also just do it in the second component instead. So in the normal syntax, it's written up top there, but it's much easier to see in this in the diagram here. That's kind of what we want to think about for the sliding equations, where the dotted line represents the sort of separation between the components of the pair. And so optics in a monoidal category A form a category of optics in A, and composition is given by sort of placing these diagrams next to each other and then working out how to write that down in the normal syntax, which is pictured up top. you don't really have to remember this. We're about to see an easier way to do it, but that's sort of the thing that this is going to be about. Those are the optics and the category of optics that we're going to talk about. And the identity wire is just where you have the pair of two identity maps. So forget all of that. We're going to talk about something else now, and then come back and see how it relates to the optics we just talked about. And that thing we're going to talk about is another construction I can do with that monoidal category A. This is going to be called the free cornering. And the free cornering of A is going to be a double category with one object. And so it's got cells with top and bottom boundary and left and right boundary, where the top and bottom boundary are elements of something called the horizontal edge monoid, which will be a monoid, and the left and right boundary, so here X and Y are the left and right boundary, will be taken from something called the vertical edge monoid, which is also a monoid. And in our double category, this free cornering of A, the horizontal edge monoid, so the top and bottom boundaries of our cells, that monoid is going to be the object of monoids in, sorry, the monoid of objects in A, because A is a monoidal category, we're allowed to do that. And then we're going to take cells for every morphism F from A to B of A, our original monoidal category. We'll have a cell in our double category with top boundary A, bottom boundary B, and trivial left and right boundary, where that means that each one is going to be the monoidal unit. We don't know of which monoid yet, but it's going to be the unit. And we'll impose equations asking that sort of composition in A corresponds to vertical composition of cells. So in a double category, of course, I can put cells next to each other vertically or horizontally, and that's kind of, each of those is a category-like composition. And we want the vertical composition to correspond to composition of those morphisms that in A, that we've sort of asked to be included, and to have some other sort of sensible things. This inclusion will respect the monoidal structure in a nice way, and so on. So we're not done defining the free cornering of A yet. So next, I'm going to give you the vertical monoid, so the things that will form the left and right boundary of our cells. And the vertical monoid is going to be polarized sequences of objects in A. Or formally, I can take the set of objects in A and assign each one a polarity, either circle or bullet, and then take the free monoid on that set. And the way that we're going to understand the elements of this monoid is as exchanges. So if I have, say, A circle tensor, B bullet tensor, C bullet, well, I'm going to understand this as a two-party exchange with, say, Alice on the left and Bob on the right, where what that sort of exchange says is that, well, Alice is going to give Bob an instance of B, Bob is going to give, sorry, A, Alice is going to give Bob an instance of A, then Bob is going to give Alice an instance of B, and then Bob is going to give Alice an instance of C. And so the circle polarity you read as kind of left to right flow, and the bullet polarity you read as a right to left flow. And now for every object A of my original monoidal category, I'm going to ask for 4 more cells of this double category. These are the corner cells. So for each A, I've got one where an A thing comes in on the left using the circle polarity and leaves on the bottom. And then I've got one where it comes in on the top and leaves on the right. And then dually using the bullet polarity, I have 2 more corners where the thing sort of comes in on the right and leaves on the bottom, or comes in on the top and leaves on the left. And then finally, I ask that these cells satisfy the yanking equations that type. So, yeah. So this is the double category specified by this data is what I'm going to call the free cornering of A. So the point of the free cornering of A, or a nice interpretation of it, is that the cells of this double category, you can think of them as arrows of A that interact with their environment by getting things in and passing things out using these corner cells. So you can imagine that I had a monoidal category with objects like dough and oven and bread. And then if I can, and things like, oh, I can knead dough into dough and bake dough and an oven into bread and an oven. And then I could form these 2 cells on the left, right? So I have one that sort of has dough, or gets dough in on the top, kneads it into more dough, and then sends it out along the right boundary. And then I could have another one that gets dough in along the left boundary, gets an oven in along the top boundary, bakes the dough in the oven to get bread in the oven. And so, you know, because it's a double category, I can compose these cells horizontally. And now instead of interacting with the environment, they interact with each other. And I can use the yanking equations to sort of put these 2 things together that way and get a morphism of the original monoidal category. And that's the cool thing about the free cornering of a monoidal category. So now we're going to come back and we're going to put those 2 things we talked about together. And this is kind of the main theorem of our work, or the main result is that if I look at optics and I look at these sort of informal diagrams explaining what they are, I can make those diagrams using the corners in the free cornering, right? So if I have a thing alpha from type A to M tensor C and a thing beta of type M tensor D to B in my monoidal category, so that would be an optic, right? Then I can put them together like this in the free cornering, and I've sort of drawn that informal diagram. And also the equations that I would want these to satisfy, these are satisfied when I draw them like that. And it's a straightforward exercise to show that this is enough to get an embedding of the category of optics into, well, the horizontal cells of the free cornering, so the ones with trivial top and bottom boundary, no wires coming in, no wires going out, where composition is put them next to each other horizontally. And remarkably, this is full. So I have a full subcategory. Optics is a full subcategory of the horizontal cells of this free cornering thing. So in particular, the one on objects of the form A circle tensor B bullet. Wow. A nice thing that this gives us. So there are nice, I showed you these sort of string diagrammatic forms of the cells in our double category, and the yanking is a sort of topological thing. And we can use those string diagrams for double categories to reason about optics. So if you look in the paper, we give a couple of examples of this, but we're not going to do it now. Instead, I'd like to talk about comb diagrams. So these have appeared in print a few times, I think, mostly Alex Kissinger. But the idea is that I want to have string diagrams with holes in them, and they're kind of like higher order string diagrams, where I'm going to put some normal string diagrams into the holes, and as long as all the types match up, I'm going to get a normal string diagram back out. And so we might picture comb diagrams like that picture above left with the empty teeth. And I can represent that in the free cornering by just having things alternate in the right order. So in the comb diagram, you see an A thing comes in the top, and then the first sort of tooth gap, a B comes out and a C goes in. Then in the second tooth gap, a C goes out and an A comes in, and then a B comes out the bottom. I can use the polarities, the thing going left to right and thing going right to left, to represent that like this, just by alternating the things along the right boundary in the free cornering. And then to put things into the teeth, I just use the corners to stick them in where they would have to go, and I get a cell out, like you would expect. So there's the only other like really satisfying formal approach to comb diagrams is in Mario's work on open diagrams. And a cool thing about this is that they're the same. So it turns out that instead of doing this sort of a co-end calculus version of open diagrams, at least for the single-sided comb diagrams, we can just work in the free cornering and get the same thing, and we can use the graphical calculus. I'll also mention that the free cornering supports some weird operations on comb diagrams. So one is I can put a comb inside the teeth of another comb to get a comb with more teeth, as you see pictured up here, where the sort of version that you would do, how you would represent that in the free cornering is given below the line. And also I could have things alternate on the other boundary to get a sort of dual sort of comb. And then if the types match up, well, it makes sense for me to push the teeth of the two combs together and sort of interleave them to get a morphism of the category. And on the right here, above the line is kind of what we would want, and below the line is how you can represent that in the free cornering. And so that's what comb diagrams are. And that's all I wanted to say. So we have lots of time for questions. So there, like one related thing, if you want to know more about these comb diagrams, of course, you can read our paper. It's called Cornering Optics, and it's on the archive and everybody's website, I think. You could read this open diagrams via co-end calculus by Mario if you wanted to compare it to the other formulation of comb diagrams. And then I'm going to advertise the work where this free cornering construction comes from. There's this coordination paper called The Structure of Concurrent Process Histories that you should read, and that's where the construction originates. There will be a journal version of it soon. And then last year at ACT, I talked about something that also uses the free cornering. So read those, cite them, and that's all.
Thank you, Chad. Question? That's really cool. Can you tell me, does free cornering have a right to have?
Oh, yeah. So, I don't know. Probably. But I don't know if it's free in the sense of being, you know, we would expect an adjunction of bicategories or something. I don't know. Yeah. Yeah.
Could you also model communication between one or two parties, like, you know, adding an extra dimension to your corners?
You can already, so if you, it turns out, if the monoidal category you start out with is symmetric, then you can already do that. Because if you start with a symmetric monoidal category, then the free cornering is a monoidal double category. And you can use the tensor product of cells to sort of, to do communication between more than two parties. And so some of this is in this structure of concurrent process histories paper, if you're interested, especially in the journal version. So, yeah.
So in Alex and the Saunders paper, where they have like cone diagrams, they interpret them in terms of star forms category.
Yeah.
And they have like this internal logic of, you know, multiplicative linear logic. Is there like some internal logic for like the free corner thing? And if so, is there any relation between this and linear logic?
The internal logic of the free cornering is probably complicated to write down because of the extra dimension, right? I don't know. I know that you have a paper where you show that there's a polycategory of combs, which is an interesting step in possibly the right direction, but I don't know.
Hi, thanks for the talk. So the string diagrams you write down.
These ones.
Maybe you said that, and these are like a string diagram for power equipment.
Yeah. So this is the structure of a pro aero equipment. We're asking for companion and conjoint structure.
Is it also another way to kind of formalize string diagram for optics, right?
Well, yeah. So these give you string diagrams for optics. Is a nice consequence for this is that the string diagrams for pro aero equipments are also string diagrams for optics. Right. Yeah.
We have formalization, which is hedges, formalization with teleological categories, sort of like half-read categories.
Read our paper. There's a section about this. Where, so in teleological categories, you sort of so what does this give you? What sort of formally is the category of horizontal cells? And one way to think of it is you freely add a dual to every object in your original monoidal category, and that's the horizontal cells, I think. And in teleological categories, you only have half of the dual structure, right? And so we give graphical proofs in the paper of some results due to Riley involving the lens laws that you cannot do using the graphical calculus for teleological categories because you don't have the other side of the dual. So somehow this is actually the right thing. Like I said.
Also the way that I think Mosso does it.
I mean, yes, so indeed, Guillaume is a yeah. Yeah, we know.
In the vertical object
the one that is X and Y.
The one with like there's two dots.
Ah, yeah, this one.
Yeah. The set that you're taking the free monoid on, it's alternatively the co-product of two copies of A0.
Yeah, sure.
Have you thought about whether you could encode mixed optics in some way by actually taking the co-product of two different object sets?
So I don't know what mixed optics are. Mario, do you want to answer this question?
So as you have it now, it's like a co-product of two copies of A0. And I was just wondering if you had, say, two categories, B and C, if you instead took the co-product of B0 and C0, would there be some way to alter the definition to encode mixed optics?
Like having to taking the objects
It wouldn't work.
So sorry, mixed optics. What I mean by that is where you have
two categories and a third category acting on them.
You would need some extra data, right? The problem is that M has to live in both categories.
Yeah, you need to.
Yeah.
We'll take one more and
can you hear me?
From the
I can hear you.
Excellent. My question is, have you thought about using the same monoid with a polarization on the horizontal edges as well? That meant motivated by, with the open gains and machine learning, sometimes we have backwards things going upwards in a diagram.
Oh, so not really, no. You can ask, so something that is worked out in this paper from ACT last year is that if your category A is compact closed, then this horizontal cells with the free cornering is also A, precisely because things can go up. And it seems like a lot of the structure, which is quite rich actually, of this category of horizontal cells of the free cornering comes from the way that you can sort of bend wires left or right and down, but never up. So I think you would be studying something else at that point, but I don't know, maybe it's interesting.
okay, I think this is a good point to thank our speaker again. This session, so there will be a bit more of half an hour than a coffee break, and then we'll be back at 4. But before that, Jay has an announcement.
If you're participating in the poster session, please put your posters up during this break. So I have some sticky things, and we're going to put them on the wall on the outside area, on the windows. So find me, and I'll give you one of these to put your poster up.
An announcement for remote people instead. For technical reasons, I have to break the call and open it again. So I'm going to kick you out, but then you can come back like when the session starts again. So don't worry if this like this. Thank you.
You couldn't be close. Yeah, no.
Where's the spot on the microphone? Okay. Oh yeah, that's
and then at random times just mutes itself. So just turn it off and on again.
And unless
they really are like.
Oh no.
But I can't do it because
unless you come in if you want to.
And then I could be Clere.
But then why do the in-person people have to give it up for the key?
I think it's good answer.
Yeah.
Yeah, I think at the inside is fine. But then it doesn't make a difference. Yeah,
So you have a. Yes.
No,
Fine, Jay.
the people in the office.
He's being brainwashed.
Oh my god, I realized what time is here.
Sorry?
Time is now.
So yeah, I'm gonna quit the call. See you in a minute.
There's no, I mean, just checking the break. I don't think.
Yeah, but it was a really nice.
I was really hoping for.
Yeah,
more
but we have to
people.
make a new one.
Yeah, so try, I mean,
That's what
there's
I
no
do.
harm in just.
Oh, other room. Oh, I don't need.
Darn
So Marta told me she couldn't do it. So
So
I guess
maybe
it
only
means
the host
we
can
can do it, but also I was hoping the solution was already out there.
I think she sent a message, right?
give me like hash structures.
There's a tiny, there's a
Well,
chance.
I mean, yeah, there might be.
So it is
For the five process.
If you throw a whole bunch of.
And then the input. 5 online.
Way less technical.
Okay, give me a second. Next one, monadic semantics.
Yeah, mostly it's actually it's worse.
Oh,
Oh, sweet.
I'll ask you just before the session starts, but just basically planning to worry about like analysis and rates and how the
So actually, I think this is the poster section.
No, there's two more talks.
Two more
She's
talks.
sharing.
And
there's a slide for the talks as well. Yeah, there's slides for the talks that you need. I can come back here like 5-10 minutes before we start if you want. And then I'll know for next time. Good.
Okay, so we have the federated architecture. Next one is algebraic property graphs.
So which ones are online?
That one. And then.
The first one is also.
I gotta leave you didn't come again.
Okay, fair enough.
So the record code, and then we have this generative model of 3 categories.
Say again. I was making sure Marta would.
Okay, so a progressive generative model of 3 categories. Create. Oh,
No, that's it.
Open all rooms.
Open all rooms.
Okay. People can join rooms, right?
Better emotions. I think people can. Just in case. In case we have more posters.
All right, because now you open them. I see. Yeah. Yes, that's a good idea because you have to close them. Yes, close them and add an extra.
Right.
This is all spinning out.
So last time Bruno was just using this sitting down, but if you don't want to like run around with them, I'm.
I guess we're unmuted
No, I'm
now.
fine. Yeah, is the next speaker online?
I'm online.
Oh, okay,
hello, great.
I just need to be given the share screen ability. Yeah.
Yeah, I'll make you co-host now, and
Okay.
then when it's time to start, you can screen share.
Okay, cool.
Malin,
Oh, there you go.
I'm down to walk around with the question mark, but last time Bruno found it easier just to do it himself. Do
There's
you-
only one though, right?
Yeah. So
Yeah,
like,
I
do you
can-
want to take this and do it?
Yeah, it's just
Why isn't this working? Where are all the participants? Why do I only see 3?
because it's only.
Oh, they're looking for someone. Oh, there we go. Okay, great. And Emilio. So my co-host. Great. Did you get any notification that you're co-host?
Yes.
Great. So you'll be able to share screen. Should be fine.
Excellent, thank you.
Are we ready to go? Should I contact people?
Okay, we're gonna mute for now, I think. Okay.
Is it? Tell me how your name's pronounced, please. Is it Nihil Shah?
I don't think you can hear it very well.
Okay. Yeah.
Cool. Oh, so this mic.
Yeah, that mic, I think.
Oh, is that okay? Awesome. And yeah, your pronouns are he, him?
He, him, yes.
Okay, cool. Awesome.
Oh, okay, yeah. So sorry, we're just getting ready. Sound good? Move that here. I think that should be it for this one, right? Okay, great. Right, that's right. Slides, everything's good. And I'll let Malin take over.
Right. Yeah. That's a good point. Ouch. Yeah.
Okay, welcome back everyone to this second afternoon session. And we'll have a bit of a shorter session now because it's really warm in here. So we have 2 talks, 20 minutes, and then we're going to all move back outside for a poster session. And the first talk of this session is given by Emilio, and he's going to talk about a co-monadic account of Feynman-Mostovsky theorems. Take it away.
Hi. So thank you to the organizers for letting me participate online. I think it's been going pretty well. This is joint work with Thomas Jakel and Dan Marsden. And I'll start with the setting. So the setting we're dealing with is a category of relational structures. So we have a set of finite relational symbols, and objects in our category are sets paired with interpretations for those relations. And then morphisms are just relation-preserving set functions. We'll also need a notion of embeddings, which is just injective set functions, which, in addition to preserving relations, also reflect relations. So this is a common setting for pretty much anything in computer science. Things like graph theory is just you choose a binary edge relation, database theory, descriptive complexity. Lots of things are in this setting. So category theorists tend to look at these structures as they really are, that is up to isomorphism. But model theorists, being logicians, look at structures with a sort of blurry lens. So that lens is imposed on them by their logic, which says that 2 structures A and B are equivalent in a logic if for all sentences in the logic, A satisfies the sentence phi, if and only if B satisfies the sentence. And this is a blurry lens because obviously if you have isomorphic structures, then the sentences in your logic should be the equivalence, they should be the same. And in those structures to be true and those structures the same. And so this is how it's sort of a blurry lens for any reasonable logic. We'll also consider a one-sided asymmetric relation, just sort of like a homomorphism, which says that if A satisfies a sentence, then B also satisfies a sentence. So for logic J, the equivalence relation J may satisfy a Pfefferman-Mostovsky theorem for a certain operation. And so basically what these FEM theorems say is that if we have a bunch of structures AI, BI equivalent in some logic for all I, then that equivalence relation behaves well, is preserved by taking products of structures or coproducts of structures, binary products, coproducts. So if you actually look in the literature, I think it's typically referred to as a Pfefferman-Bott theorem without the Mostovsky, but actually Mostovsky proved the product theorem like 10 years before Pfefferman-Bott proved it. It's one of those examples of something between during the Cold War. But in general, for an operation H on some categories of models and logics J1 through Jn and J, we have a Pfefferman-Bott theorem of this form where A and B, AI, BI are equivalent in the logic Ji, implies that for this operation, applying the operation to all the different models, you get equivalent structures in the logic J. And these sort of Pfefferman-Bott theorems are sort of key ingredients in a lot of algorithmic meta-theorems, including Courcell's theorem, which says that graphs of bounded tree width, any MSO definable property has some efficient linear time algorithm. And the way it sort of works is building up the structures using these various operations that build up bounded tree width structures. So the task here is how can we prove such statements categorically? I mean, it's actually kind of surprising to me that this is products, coproducts. It's something natural to state in the setting of category theory, and yet, as far as we know, no one has up until this point actually tried to prove it categorically. So the way we'll actually do this is using a recent development, which is like comonadic semantics for logics. There's a whole research project around this. And in particular, we're going to focus on the example of first-order logic up to a certain quantifier depth. And the comonadic semantics for this is captured by a so-called Einforce Versay comonad. So this has some game theoretic interpretation where 2 players are trying to show that the 2 structures are equivalent logic and they're choosing certain witnesses to existential quantifiers. But for us, you can keep that intuition in your mind, but since we're category theorists, it just goes directly to the definition. So given a sigma structure A, we can create a sigma structure on EK of A, which is just non-empty sequences of elements in A, less than or equal to K. And then we have our co-unit, which just returns the last move of the play, and our co-multiplication, which just returns prefixes. So people recognize this as the prefix list comonad or the non-empty list comonad. But we're on relational structures, so we have to say how we actually lift the relations. So if we have a bunch of sequences S1 through SR, then we say that they're related if and only if one is the prefix of the other, and their last moves are related in the original structure. So it's a theorem by Abramsky and myself that if you have a co-Kleisli morphism, then that's equivalent to preservation of existential positive sentences. And if our structures happen to be finite, then our two structures, Kleisli isomorphism, characterizes not equivalence in first order logic up to quantifier type, but actually a stronger logic where we add quantifiers that count the number of elements that satisfy that quantifier. So hash LK denotes having first order logic with quantifiers of the form there exists at least n witnesses to this X quantifier. And I should note that typically logicians consider logics with equality, but we actually are only going to deal with logics without equality, and then I'll explain at the end how we can add equality. So the task is to prove that using this EK, this comonadic semantics, a Pfefferman-Bott theorem, for a certain operation, and for an example operation, we're going to choose the coproduct operation. So recall that the coproduct of two relational structures can be encoded as pairs AI, where I is either equal to 1 or 2, and then AI is in that component. And then relations are defined in the obvious way. So if you have a bunch of these pairs, then they all have to agree on what component they're in, and then they have to be related in the original component. Now, a key to this is then we just need to have some distributivity between our comonadic semantics, first order logic, and this coproduct operation. So the way we define a collection of morphisms for every A and A1 and A2, which takes a sequence of pairs, and then depending on the last pair, it chooses what component to send the sequence to. So if it's in the first component, then we just take this sequence and just remove all the other elements in the other component, and then we get a word or sequence in EK of A1, and likewise for EK of A2. So since this relation here, AI to sub EK to BI, is by definition just the existence of a co-Kleisli morphism, to actually get this Pfefferman-Bott theorem for preservation of existential positive sentences, we just need to compose with the coproduct of F1 and F2. So we are pre-composed with the by kappa with F1 and F2, and then that allows us to get a composition, a co-Kleisli morphism of the right type, and then we can conclude from this theorem here that we in fact get coproduct preserves the preservation of existential positive sentences. For the counting, we need to, that's characterized by Kleisli isomorphism. So we need to show that if F and GI are, so GI is just a morphism where BI and AI are switched. That's a typo. If they are inverses, then we have to show that the coproduct of these two morphisms pre-composed with kappa are also inverses, but that's actually just equivalent to kappa satisfying coherence axioms with co-unit and co-multiplication. So, and that's what's called in literature, kappa has to be a Kleisli law. So if we just require that we have a collection of morphisms of the right type, then we get existential positive. But if we also require this Kleisli law, then we are able to prove a Pfefferman-Bott theorem for that operation for first order logic up to k with counting quantifiers. So in general, if we have an operation H with comonads capturing logics and a Kleisli law, and so notice here that these comonads can be different, capturing different logics, then we immediately get that if AI, BI preserve the existential positive sentences, then we also get it for the compound structure, and the same for equivalence in the counting quantifier logic, the logic extended with counting quantifiers. So, but how do we actually, so we have this sort of Goldilocks problem. We've characterized something weaker than our logic, existential positive fragment, and we've characterized something stronger than our logic, logic extended with counting quantifiers. But how do we actually define the semantics for the unaltered logic, the full logic? So we can define the semantics for first order logic up to quantifier k in terms of the Eilenberg-Moore category, the category of coalgebras. So the category of coalgebras for E sub k intuitively is just forest-shaped covers of objects in the relational structure. So the way you can see this is that if we have our coalgebra, then since these are just sequences of elements, we can obtain an order on the elements just by looking at their image under the coalgebra map. Alpha A is a prefix of alpha A prime. And then the actual axioms of co-unit and co-multiplication actually determine that this is a forest order. And then the fact that we have the relations that we put on EK, and this is a homomorphism, gives us that it's actually a cover of the relational structure. So because we have this tree ordering or forest ordering on the elements of A, then we can pick out a certain subcategory of paths, a full subcategory of paths inside our category of coalgebras. And that just means that this relation that we defined here is a finite chain. And so we can think of embeddings into another coalgebra as just picking out paths in this coalgebra. And if we look at these as plays in the game that characterizes first order logic equivalence, then if we consider a co-free coalgebra functor, then a path embedding into a co-free coalgebra just picks out plays in that game. And so if we want to define semantics for our logic in this category, we show that we define this relation A equals B sub EK if there exists a span of this form, where we have our co-free coalgebra applied to A and B, where F and G are pathwise embeddings, which all that means is that any path in the domain must be transported to a path in the codomain, and then open maps, which says that if a path can be extended in the codomain, then it can be extended in the domain. So many people who are familiar with this would see this as a sort of open map bisimulation. And so actually a lot of, like in the particular case where we choose our comonad to be one that captures modal logic, this in fact recovers bisimulation. But this shows that actually equivalence in first order logic is characterized by some higher categorical notion of bisimulation. And so this path open map lifting property can be seen diagrammatically as, so we have a path in the codomain of F, and then we can extend it to a path in the domain. And so this is a theorem by Ramsey and myself that says that if A and B are equivalent under this relation, span of open pathways embeddings, then they're equivalent in first order logic up to quantifier rank K without equality. So going back to our running example of the coproduct operation, to get an actual categorical proof that coproducts distribute over this first order logic equivalence, then we need to produce a span of the right type. And given sort of these free coalgebras, we have to have some way of combining them using some lifting of the coproduct operation to the Eilenberg-Moore category. And that is isomorphic to the just having the free functor and the coproduct inside. And then we also need to fact that if these are both spans of pathwise embeddings, then we also have to have that this composition is a span of open pathwise embeddings. So we've shown that it's sufficient to just assume that if F1 and F2 are embeddings, then the lifted operation is an embedding. And then to get the openness, we also need the fact that if we have a path in the coproduct structure of our lifted operation, then there has to exist some minimal decomposition of this path into the constituent paths for each of the components. And so it's a decomposition that's clear because we can just take the E and then decompose it into the various paths for each of the component and some mediating map. For it being a minimal decomposition, it's sort of the typical categorical thing. So any sort of other decomposition, we have some mediating map that allows us to go from that decomposition to this decomposition. So since our comonad EK preserves embeddings, we know from various categorical nonsense that we can actually compute this lifted operation as a certain equalizer in our category of coalgebras, where we take, basically what we do is we take the cofree structure on the coproduct structure, but we can't just do that because we're not respecting the coalgebra structure of alpha-1 and alpha-2. So we have to take a substructure which is of this cofree substructure, of this cofree structure, that is compatible with these original coalgebras. And basically what that means is, we call this cofree substructure is just a bunch of different elements with 1 or 2 in the front telling you which component we put the elements from. And then we require, the substructure is just the substructure where when you take the restriction to the component in the first component, then it has to be in the image of our alpha-1. And similarly, if we restrict to all the elements appearing in this word that are in the second component, then they have to be in the image of alpha-2. So you can think of this as an interleaving sum of paths of these two coalgebras, these trees, and then we can sort of interleave going between the two paths in either tree. And so what's interesting about this is actually, you can see this as this diagram is actually dual to the quotient construction of a tensor product of vector spaces. So if we consider this as like, the analogous thing is if we have a free vector space on the Cartesian product, then if we take a quotient, so some co-equalizer, that is compatible with the vector spaces of the original that we applied the free vector space to. So that means closing under equations that's about scalar multiplication and addition, then that's exactly the definition of a tensor product, a concrete definition of a tensor product in the category of vector spaces. And so this insight allows us to dualize some ideas from bilinear maps in commutative monoid theory, in particular for the phi vector space, but we're just using the abstract stuff for commutative monoids, which allow us to reformulate the axioms in terms of the lifted operations to axioms about the ordinary operation. And we want to do this because we don't just care about coproducts, we care about other operations. And so if we don't have to actually figure out concretely what this equalizer is, what this coproduct operation is, then we just have to, it would be nice to just have to analyze the ordinary operation of the relational structures. And so dualizing some ideas about bilinear apps, we show that if the operation preserves embeddings, then the lifted operation preserves embeddings. And then we can reformulate this axiom here, this minimal decomposition axiom that says that if any function from a path coalgebra into these inside of our ground category commutes like this with, notice we only have our kappa and we only have the ordinary operation, not the lifted operation, then any function that satisfies this diagram must also have a minimal decomposition where these are in fact path embedding. So we've finally gotten to an abstract version of the Pfefferman-Bott theorem for the full logic, not the logic with counting quantifiers or the existential positive fragment, where we have given the same assumptions. So we have an operation with comonads that captures the logics, and we have a Kleisli map satisfying, and H preserves embeddings. That's this axiom here. And H satisfies a diagram similar to this, but obviously instead of the coproduct operation, we have our operation H. Then we get that if AI, BI are equivalent in logic JI, then the compound structure is equivalent in J. So I mentioned that we actually care about, we've only proved it for logics with equality so far, but to add equality, we actually have an interesting application of the theory of relative comonads and monads. And so in a relative monad, a monad is, or comonad is in particular endofunctor, but a relative version is where you weaken the endofunctor requirement, and we just consider morphisms where we sort of lift it to a functor from a base category to another functor. So to add equality, we just consider a functor which sends a relational structure to a relational structure where we have an additional binary relation that interprets this binary relation on a structure as just equality on that structure. And then we can consider EK composed with TI as a relative comonad over R sigma super I. And since this translation functor easily commutes with the coproduct operation, we actually get first order logic at the original first Pfefferman-Bott theorem, which is coproduct operations with first order logic up to quantifier rank K. Initially, this seems sort of like a hassle to actually have to use a relative lifting, a relative comonad for this, but actually, it's actually kind of a feature of our framework because logicians tend to study logics with other sorts of interpreted relations, not just equality, but for example, they a recent paper in Lick says is a study of first order logic with a connectivity relation. So if we have a graph, then the connectivity relation will be interpreted for each graph as just these two elements are connected in the graph. And then we just, and this logic is in fact more expressive than first order logic, because you can prove that first order logic can't define this connectivity relation. Then we just have to consider a translation function that interprets the additional connectivity relation as exactly just those connected components. And so I'll say that products are actually a lot easier in this setting. So it's very easy to show the Pfefferman-Bott theorems for products because we have cofunctors are in particular right adjoints. So when we go back to this lifted operation, the lifted operation for the product will just be products of coalgebras.
Can you wrap up?
What?
Can you wrap up?
Yes.
I guess this is the last slide anyway. I can't really see the slide.
So yeah, basically there are many other comonads to explore. It's not just first order logic up to K. There's one for K variable logic, modal logic, many others. It's been a very active research program. And the general abstract setting for all of these comonads are axiomatized by a recent paper in 2021 by Ramsey and Regero, which sort of axiomatizes the idea that all these comonads give you tree-shaped covers of objects. Yeah, so that's all I really have to say. Thank you.
Thank you very much. We have time for one or two quick questions. Okay.
Hi. I saw that your operations on your structures only ever have finitely many inputs. But is there any hope for also getting like filter products in this way, or?
Oh, yeah, you can do. Yeah, I just used finite arity operations because it's easier to put on the slide. It works perfectly fine for infinite operations. I mean, you obviously have to prove the axioms, but yeah, the framework works perfectly fine with infinite operations.
All right, then I have another question. So these comonads you consider, these are all parameterized with this K, right? And the results you prove show that, for example, that these capture logical equivalence with depth up to K.
Mm-hmm.
Have you considered maybe kind of enriching what you're doing, not in the technical sense, but like moving to something like graded comonads, which will then hopefully allow you to also get results that speak about the interaction between these different logics?
Right. Yeah, so we have considered more interesting gradings rather than just like an index K to model some things that are second order, but it never seemed to have worked out very well. But yeah, I'd be very interested if you have any ideas on how to grade it, actual graded comonad, rather than just something like an index family of comonads.
Right, thanks.
Yeah.
Yeah, thank you very much for a really nice talk. One quick question, there's also like what logicians or model theorists will consider this homomorphism preservation theorem, which is in a way a version where you would just say for a given formula, it is preserved under homomorphisms of all structures, if and only if it's logically equivalent to an existential positive formula. So it's in a way reversing the quantifiers that you have. Is that, was there any relation to that you considered?
Yes, so I haven't specifically considered it, but other people in our research program have, and they've actually proved Rossmann's homomorphism preservation theorem using comonads. It was actually quite a long bit. There was various different, and they proved generalizations to, they recovered the various things like for modal logic, you get the Van Bentham theorem. And so there's various axioms that show when you can get a Rossmann homomorphism style theorem. And that's specifically worked by Samson Abramsky and Luca Reggio. So people have worked on this, yeah.
Okay, thank you very much, Neil.
Yeah. Thank you.
Does this work? So this is audible. Is it on? Are you even? I think I should turn it on first. It is on.
Where is it now?
Okay. Okay.
I know it doesn't work. So I'm gonna try to open up your.
It's that one.
Oh, this is something.
You can do Control L.
Okay, so our next speaker is going to be Ezra Sun. They're going to be talking about lax liftings and lax distributed laws.
Yeah. Let's see if it works. Yeah, it works. Okay.
Okay, take it away.
Yeah. So thank you, Manon. So I will indeed be talking about lax liftings and lax distributive laws. I have some preamble. So this is material that mostly originates from my master's thesis. And so I would like to here acknowledge my supervisor, Ide Venema, who also very much encouraged me to find an audience for this material. So you can either thank or blame him for the fact that I am here right now. So let's start with the liftings. So what's a lifting? I'm going to paint a very general, sort of overly general picture where we have some kind of functor on the bottom, and we have some kind of adjoint situations. And we want to see if we can lift this functor to these categories living above in a way that some things might commute here. I don't even want to specify what's going to commute, but some things might commute. And that's then a lifting. And you can imagine for yourself all sorts of situations where you might be interested in such a thing. These have been studied, like I think, like quite extensively. And going back to like Beck's fundamental theorem, or like a fundamental theorem by Beck, which says that if situation is where you have some endofunctor on a category C, and you look at like the Eilenberg-Moore category for some monad over it, then if you want to lift such a functor, it's the same as giving a gadget of this type. So this is a distributive law of your endofunctor over the monad. And you need to add some conditions, and you might also want, if you know that this is actually already a monad, you can also lift it to be a monad over here if you have some additional conditions, and there's all sorts of things you can do. And then shortly after Beck had published this, like people were onto it, and Mulry said that you can actually do the same thing for Kleisli categories, which is nice. And then you can vary this however you like. You can do it with some weak monads. You can get whichever kind of adjoint situation you want. And now I was interested in a very particular case, which is this case, where at the base we just have sets, and our adjoint situation is with rel. And now I need to be particular here. With rel, I mean that the objects are sets and the morphisms are relations, and the composition is relational composition. And now this is actually a special case of the Kleisli picture, because as you may or may not be aware, this category of relations is actually the Kleisli category for the power set monad on sets. And so, yeah, so we're interested in like, when can we lift this functor up to rel? And then you might be thinking, well, but if this is a particular case, then we already have it from Mulry, right? He told us, when can we do this? And you might say this, but there's a problem, which is that we also know that there is at most one solution here. And so there might be various kind of phenomena around this functor that we're trying to capture. And if there is at most one solution, then there's at most like one phenomenon we can capture, which is not very nice. And it gets worse because like existence is definitely not guaranteed. So your functor has to preserve so-called weak pullbacks for this to exist. And if it doesn't, then there is just no such solution, which is not very good. And so how can we fix this? Well, we make some things lax, right? If we make it lax, then we have more freedom to wiggle around, and so we might get existence even where the strict version doesn't exist. And that's what I'm going to be explaining right now, which are so-called lax liftings. And so we fix our endofunctor, and then like I call my lifting L, and it is a lifting if it satisfies some properties. So it has to laxly preserve composition. It has to laxly preserve graphs and also converse graphs. This is maybe a bit strange. You can put it diagrammatically like this. And so this is like part of your adjoint of your adjunction. And the point is really that there is sort of no principled way of distinguishing between these two. Like rel and rel op, they're just isomorphic categories. So I don't want to like elevate either of these to the definitive one. So I'm just saying in both cases, I need to laxly preserve the graphs. And I also want monotonicity because my relations are nicely ordered. So I want to know that my lifting preserves this ordering. And these are these are not new. They've also been studied quite a lot, and they also keep getting reinvented and keep getting new names and slight variations on them. So it's a bit messy. This is actually kind of something which generalizes various kinds of things. It's a bit messy, but I'm also going to want to give a very short example here, maybe give you some picture. So our functor is very simple. It's just going to take the product with some set of labels. And I'm going to say that this set of labels, it has some post-set structure on it. So it's an ordered set. And then I can lift my relations by saying, well, I take a label point and a label point, and I relate them if like the underlying points are related, and also my labels are increasing. Yeah, so that's an example, but there's like lots of examples, and we will be seeing some examples later on in the talk as well. Okay, now, if you remember from some slides ago, we had this Beck's theorem, this Mulvey's theorem that said that these liftings, they're always equivalent to giving some kind of distributive law. And this was sort of the big theme, and this was then also the point of departure here, where we have these nice liftings which already exist. Another question is, do these also come with an equivalent notion of a distributive law? And the answer is yes. That's the sort of the moral of the story. There is some notion of a lax distributive law which corresponds exactly to these liftings. And now a distributive law, like on its own, like strict version, it's always a natural transformation. In our case, it's not a natural transformation, but it's like laxly natural. So we have some collection of maps which satisfies this like lax naturality condition. And then we also need, as always with these distributive laws, you need some conditions as well. But if you formulate them right, then you do get the nice correspondence between the lax liftings and the lax distributive laws. So this theme which ran through these liftings is the story of liftings, which is that liftings and distributive laws are two sides of the same coin. It nicely continues to hold. So that's sort of conclusion one of the story. And this is sort of like halfway in my presentation. And so what I'm going to do now is I'm going to step away from this more abstract view, and I'm going to look at two functors in particular, and I'm going to investigate what kind of liftings these functors have. And so the first one is going to be the neighborhood functor. And what does it do? Well, it's just a double power set functor. So you have some, so this is like a neighborhood system here where we have three neighborhoods, and one of them has these 2 points, one of them has these 3 points, and one of them has these 2. And now I've not given all the data yet because I've told you what it does on objects, but it's very important what it does in morphisms. Because I say here the double power set functor, but which power set functor? Because there are two power set functors. There's a covariant one and a contravariant one. And if you take the covariant one, this is a very nice functor. But we take the contravariant one twice. So what you do is you map some neighborhood system to those sets whose inverse image is in there. And this makes this a very nasty functor. It doesn't play well, and importantly, it doesn't preserve weak pullbacks, which means that it doesn't have any strict liftings. And so maybe this is one of the nice cases where our lax liftings come to the rescue and give us some interesting liftings where the strict one couldn't do it. Well, let's see. So let's try to find one of these liftings. And so our liftings, they need to have several properties, and one of them is like monotonicity. You need to preserve the ordering of the relations. And I'm going to be very lazy, and I'm going to say, in order to enforce this, I'm just going to make it constant. So if I know what my domain and codomain are, I'm just going to ignore what the actual relation is and just always make it the same relation between the domain and codomain. And so what can I do? is I can find some property of these neighborhood systems and say, well, I just want that one to be preserved along my lifting. So I'm just going to relate all of the structures where if this one has the property, this one also has the property. Or maybe I want it to go the other way around. I can choose. And so this, I mean, this is going to work if we can find a good property. So of course, the first property you might be thinking about is that you want them to be non-empty. It doesn't work because, and this is why the neighborhood functor is such a bad functor, is that you can map using a graph a non-empty neighborhood system to an empty one. Which means that if we use this property, we're not going to be preserving our graphs. And this was another one of the conditions of our lifting. So we need to always preserve the graphs. And so this property is not going to work. But containing the empty set will work, because this one is preserved and reflected along graphs. So it's perfectly nice. And also containing sort of the universe, like the set of states of your domain versus your codomain. It's also going to work. And so in this way, we can find some liftings. And now the sad news is that that's all you can do. So in fact, there are no non-trivial liftings for the neighborhood functor. They're all constant, and they're all saying, right, I want to preserve and or reflect this one, and I want to preserve and or reflect this one. And so it's a bummer, because we had hoped that our Lex liftings would give us more information for this neighborhood functor, but they're not going to do anything interesting either. But there are functors for which they do. And this is my second case study, which is the monotone neighborhood functor. And it's a variant of the neighborhood functor. It's actually quite a simple variant, because you just take the upward closed sets. You can also think of it as saying, well, these are this double power set is also functions from the power set to the Boolean algebra 2. And then you want this to be a monotone function. It's equivalent, and that's also saying, why is it called the monotone neighborhood functor? Well, it's for that reason. And this is just a subfunctor of the neighborhood functor, so morphisms we do the same thing. And this functor also does not preserve weak pullbacks. So there is also no strict lifting of it. But there are lax liftings. I also want to give some intuition for why we might be interested in this functor, because it arises very naturally in game logic. So if you want to give models for game logic, then Coalgebras for this functor are very good. And the intuition is that the neighborhoods are the moves for the first player, and then the points are the moves for the second player. So the first player first picks some neighborhood which says, and then hands over the power to the second player, who can, but the first player, she gets to dictate what are the moves that the second player can make. And now, because we are very much interested in we are on the side of the first player, it means that if we give the first player, the ability to give player 2 more power, right? So we take the upward closure of this. So then the first player can also say to the second player, oh, you can choose from these 3, which is never going to do that, because it's always advantageous to restrict the power of player 2. So the monotonicity is sort of not really changing the game if we are taking the perspective of player 1. Okay, so this is some intuition for this functor. And now I'm going to give you a lifting for it, which is this horrific expression. So it's saying for every neighborhood on the left, you have a neighborhood on the right, such that if you can make a move here, you can make a move on this side. But it's a bit ugly. But I can maybe give some intuition with this picture. So if we have some relation here, the relation is indicated by the letters. So those labeled with A are related to this one. Those labeled with B are related to the one labeled with B, and similar for C. And now these two neighborhood systems, they are related by the lifting of this relation. Because, I mean, we can just do one for fun. So if I choose this move, I can copy it with this move, because if I go here, I can choose either of the B points, and if I go here, I can choose the C point. And so you can have this sort of back and forth kind of strategy. And this lifting, it also, so it's I didn't come up with this. It already existed in, like I said, in game logic, also in monotone model logic. It was like used and studied. And it's also sort of a natural thing to come up with once you start working with this monotone neighborhood functor. But it was always a bit kind of ad hoc, where we didn't quite know where it was coming from. But now, so in this work, I show that this is actually the smallest possible lifting for this functor. And for lifting, it's good to be small because it means you distinguish more points. And so this is definitely a case where our lax liftings, they give us more power than the strict ones, because this is a very interesting kind of lifting. It does nice things, and it's intrinsically lax. Yeah, and that's the end. So thank you.
Thanks for the talk. So, what are kind of the applications you intended with these liftings? Like, what are they useful for?
Yeah, so there's that's a very good question. So my main intention when I started studying these was to give was to study like bisimulation and simulation for coalgebras, because the strict liftings, they're sort of very widely used to model bisimulation. And so, for instance, this lifting for the monotone neighborhood functor, it can be used to study bisimulation for these monotone coalgebras for this monotone neighborhood functor. And if you look at all of like the proofs involving like these liftings for bisimulations, you see that the laws for the lax liftings, like these inequalities are the important ones. These are the ones that are always used. And so it was sort of came very naturally to say, well, all of the things that people are doing for like strict, strong bisimulation using these strict liftings, I mean, we can like do all of that, but with these lax liftings, and then we get bisimulation in more cases, but we also get simulation. So, I mean, I think it's quite powerful.
Yeah, great, thanks.
I think you actually sort of answered my question, but what is the relationship precisely between this minimal lifting that you presented and a bisimulation for coalgebras of the double power set functor? Because it sort of seems very similar.
Yeah, so I think a bisimulation for this double power set functor is a relation between your two coalgebras, such that if you unfold, so if you apply your coalgebra map, then their unfoldings are in the lifting of your relation. And so this is so this is essentially how you use these to get bisimulation.
More questions?
The inequality you use in the lax distributive law definition comes from the fact that P of X has process structure, right? You're using the set inclusion.
Yeah, yeah.
Do you know what's the abstract structure you need on this monad P to talk about lax distributive laws in this sense?
So I don't know, but I'm very curious. I think, yeah, no, so I don't know. but it's a very good question, and this is like one of the things that I'm really wanting to know more about.
Okay, let's thank you again. So we have now the poster session with posters being on the outside of this greenhouse up there. And there's also online posters as well, which are presented in breakout rooms of the overall Zoom call. So if you want to see one of the online posters, join the Zoom call and join the breakout room. And yeah, there's lots of posters, even too many to fit on one slide. So go and see the posters, and also there's going to be a drinks reception as well, just kind of starting around about now for the posters as well. So we'll head outside.
Mute so that people know.
Oh, great. I think I can share my screen now. Thanks.
Oh, sorry. So we've been talking to you, Shen, but I guess we did it with body language. Right. So Marta's wondering, make people co-hosts. Who else needs to? All the guests, I guess. Instead of, yeah, right. She has to co-host.
So I guess it's the presenters that need to be. I don't know. Maybe they don't need to be co-host. Maybe they just need to be
Yeah, I think
Maybe
they
there's
need to be co-hosts, I think.
They need to be co-hosts, but now I'm the host, so hopefully I can now go through and do that.
You need to bring people back to the main session to do that. Apparently. Somebody's not clever enough to do it from the room.
I'm not moved. Okay, she's going to find out. Yeah.
Hi, everyone on Zoom. I just wanted to ask if there is anyone on Zoom who wants to join a breakout room but is unable to join a breakout room, and whether they want me to try and assign them to a breakout room.
Yes, hi, and
Hi, do you want to get to a breakout room?
yes, exactly. I don't know the name of the room. I'm Sergei Solovyovs.
Yeah. Are you presenting or are you
No, I'm just a listener.
Okay, cool. And which one do you want to go to? We've got there's one poster on probabilistic generative models, one on algebraic property graphs, one on monadic semantics, and one on Frobenius structures.
Oh, okay, maybe it will be Frobenius structures.
The Frobenius structures. Okay, great. Let me do that for you. So there you go. Hopefully you should be sent over there. Okay. Anybody else who would like me to assign them to a room?
Today we're going somewhere with water.